and you hit it on a ceramic target, and it evaporates and it deposits material on your substrate. That substrate is at high temperature, and you can basically grow this layer by layer. And that's why it is atomically precise material synthesis. And as you will see in the next couple of minutes, that precise material synthesis becomes very important. And so you can start to create, using these kinds of approaches, epitaxial heterostructures. Using precise quality substrates, you can start to grow these materials with atomic scale precision. You can manipulate these structures at the scale of 2 angstroms, which is 1/2 of the unit cell. These are all atomic resolution images of this material. Okay. Now, the first piece of data, I think this is an important piece of data because it tells you that indeed you can manipulate magnetism with an electric field, which a lot of people will tell you, oh, look, that's not easy to do. Indeed, it's not easy to do. So we have this material, the multiferroic, here, 50 nanometers of that. Then we build a magnetic structure, which is called a spin valve, which has got a ferromagnet separated by a layer of a metal. And what you do is you can measure the resistance of this layer as a function of the magnetic state. And you can see that this is the magnetic data for that. You can see that these are poled, magnetized the same direction, in the opposite direction, but in between they are poled, magnetized in the opposite direction to each other. That's the spin valve that you see there. Okay. And you can make very small structures with e-beam lithography. Now, when you apply an electric field, you can see that there's a big difference between -2.5 and +2.5. Indeed, we're manipulating the magnetic state of this layer, which is magnetically coupled to this multiferroic layer. Okay, so we can then show that by simply shrinking the thickness of the multiferroic from 50 nanometers to about 20 nanometers, we can reduce the voltage significantly. This is an image of the ferromagnet, where you can see by applying -500 and +500, it became black to white or left to right magnetization. That's the corresponding ferroelectric hysteresis. So you now have a material where you can switch both the ferroelectric order and at the same time simultaneously manipulate the magnetic order. This guy did much of this work, Bhagwati Prasad. He's now a big professor at IISc in Bangalore. He just went back a couple of years ago. So he did a fantastic piece of work with us here. Okay, so this is a quick summary. We can manipulate the energy landscape. In Landau physics, this would be called the Landau double well structure. You can manipulate it with crystal chemistry. You can switch the ferroelectric. This is 10 nanometers, a few tens of unit cells, at an applied voltage of about 200 millivolts. You can manipulate its mechanics. You can also manipulate interfaces with this. All very interesting. Then based on that, we built this kind of rudimentary structure. It took us a while to do this, where we had this full the ferromagnet attached to the multiferroic. These are the metal contacts for the bottom. And what happened was when you switch the multiferroic back and forth, the resistance of the platinum was changing back and forth, not by a huge amount, but it's changing by a very small amount as I was switching it back and forth. That resistance is the change due to the inverse spin Hall effect. I'm going to get into this in a little bit more detail in the next 5 minutes or so. Okay. So this was important because it now gives you a way to read out a magnetic state. Otherwise, you would have to do a magnetic measurement or do optical measurements. Okay, now a little bit on the spin to charge conversion. That's this layer that I talked about. We need to do it at 100 millivolts, which means the efficiency of this conversion has to be significantly high. Just to give you a number, for platinum, that efficiency is 0.1. I'm going to show you data in the next couple of minutes of materials which are 30 to 50 times larger than platinum. Okay. So a little bit of the physics, and I promise you I won't bore you or drown you with all the details, but this is just to set the context. So if you have a structure which has a ferromagnet in contact with a metal, a spin orbit coupled metal, the spin Hall angle, theta, is the ratio of the spin current to the charge current. And therefore, from that, you can define a spin orbit torque efficiency, psi, which is just the eta. Eta is just a transparency factor. Typically, eta is 1 times theta. Okay. So the efficiency depends on the electronic structure of the metal. Okay, and you typically use a heavy metal because spin-orbit coupling plays a big role. That's why this is called the SOT efficiency, spin-orbit torque. Spin-orbit coupling in that metal plays a big role in manipulating the magnetic spins. Now, here's some comparisons of heavy metals versus, topological insulators. I'm sure you guys have heard about this. The efficiency of most heavy metals is like 0.1 to 0.2. And now, unfortunately, this is too much of Hamiltonians, but this is all you will see. This is the sigma, the spin conductivity. It has this rather complex-looking equation. There are two parts to it. One is this omega. That's called the spin-Berry curvature, which is a very sophisticated property of the band structure of the material. And then the other term that is really important is the degeneracy of the band structure. And for large Berry curvature, you need almost degenerate electronic bands, which in many cases appears in the case of heavy metals. Okay, so what we have been doing is to use epitaxy again to create perfect interfaces between oxide-based spin-orbit coupled metals and ferromagnets. And by doing so, this is an example of strontium iridium oxide, which is supposed to be a topological insulator, very exotic electronic properties, and lanthanum strontium manganese oxide, which is a ferromagnet. You can see that when you grow these perfectly, atomically perfect, the efficiency actually goes up as you make it thinner and thinner. This is the SOT metal. You make it thinner and thinner, it gets even better. And so we said, hey, that's a very nice idea. Let's start to make epitaxial structures rather than just growing polycrystalline materials. That brings us back to this device I showed you from this Manipatrani paper. What we were talking about in that paper was to have this device where you have the ferromagnet, and this is the magnetization pointing this way, and the magnetization pointing this way. In turn, that changed the direction of the spin-orbit coupled current from going to the right, going to the left. And you can see I have inverted the sense of the current, which is a building block to make a logic element. And typically, that's what you would do using transistors. You make an adder circuit, you need 32 transistors. And we are saying, hey, we could do the same thing with this. Now, what we realized was that our original structure was incredibly complicated with this ferromagnet. We were saying, maybe it's possible that I have my multiferroic and I read out the spin, the state of the antiferromagnet using the inverse spin Hall effect, but in this case with the ferromagnet, with the antiferromagnet. And indeed, you can do that. This material, bismuth iron oxide, is a chiral material. It has a double well structure. It's ferroelectric. But when you switch the polarization from red to blue, the L also will also change. And so you can basically manipulate the magnetism. And some theoretical calculations indeed showed that the total spin current, which is shown here on the y-axis, changes as I go from left to right, which means I could manipulate the spins that way. And so I had a student who is now making a huge amount of money in McKinsey. He did a beautiful thesis. He had this bismuth ferrite, which is shown here. He put platinum contacts on this, and then he switched it electrically, and you could see it went from white to black. But what we did was then run a current through the platinum and launched spin waves through the multiferroic. These are called magnons. These are spin waves. They could be ferromagnetic or antiferromagnetic. In this case, they're antiferromagnetic. What he then did was to pick up these magnons at this platinum and sensed it with the inverse spin Hall effect. That's this voltage signal that you see here, that indeed you're getting a voltage signal from the inverse spin Hall effect. What was really surprising is that when you switched the polarization state, that voltage flipped direction. It went from plus 40 to about minus 40. Then we said, wow, this is very interesting. We could follow the hysteresis of the non-local spin Hall voltage, which is shown here. That follows the ferroelectric hysteresis of this material. And the key here was that when you switch the ferroelectric state, the antiferromagnetism in this material also changed. So we were manipulating spins with an applied electric field. That's what the real answer was. We said, great, now we can go back to what we know about oxides. We replaced the platinum with strontium iridium oxide, and sure enough, we got an output voltage which is about 20 times larger than platinum. The blue data is for platinum, about 40, 50, maybe 100 nanovolts, while for the oxide, epitaxial oxide spin orbit metal strontium iridate, it was of the order of about 1500 nanovolts, 1.5 microvolts. And very soon I'm going to show you that, oh, it can be even more larger. What we found was that if we reduce the spacing from 1 micron to 100 nanometers, so this is 10 nanometers, this is 100 nanometers, that voltage signal kept on going up. And by now we have approximately 10 millivolts of output voltage for a 10 nanometer device, all the way from 100 nanovolts to about 10 millivolts. And ideally, we want to get to 100 millivolts of signal. So the key here is that by using the principles of condensed matter physics, designing the electronic structure of these materials, using the principles of material science, where epitaxy gives you perfect interfaces, you can start to design electronic structures and get amazingly different properties than what you would in the case of a polycrystalline material. That voltage output is what we are looking for. It should be 100 millivolts. So we are not very far from there. In the next few years, I think we'll get to that number. As we do this, one of the big questions on the physics side has been, how do you understand spin transport? And for example, in a superconductor, in a standard BCS superconductor, you have electrons which pair with each other, right? And the coupling is mediated through the lattice by phonons. The question is, can we go in these kinds of spin transport systems from diffusive transport, which is kind of meandering, to ballistic transport, where the spins go from one electrode to the other, like basically a bullet? In that case, one is expecting to see significantly different physical behavior. We can start to have the equivalent of superconductivity. You can have spin superfluidity. Lots of new things will start to happen when you can go from diffusive transport to ballistic transport. Nobody has shown this yet. So if you're going to do research, this would be a great area of research. Okay, that brings me to the last part. This is just the conclusion. So what are we trying to solve from a more applied perspective? We want to bring the energy down. We want to go to about an attojoule. This is where we want to be. This is in femtojoules. We want to be latency of about 100 picosecond. That's where many of the applications are. And so you want to be very fast, very low energy. What I've shown you today is that these new materials, multiferroic materials, in principle can get you down to the 100 millivolt kind of voltage range, which basically translates to energy scales of the order of tens of attojoules. But the big new discovery, I would say, has been that these oxide materials, where the spin orbit coupling can be significantly manipulated, can give you much larger efficiency of conversion from spin to charge. So let me finish up with a slide that one of my daughters made, which captures the essence of this, not the black screen. How do you go from global techno-economics to spin orbit coupling? So I hope I've shown you that you can go from global economics, trillions of dollars worth of markets, go to the technologies, in this case, AI, machine learning, go one level lower to energy efficient electronics. But you don't stop there. You can go in and say, let me use this as a way to design new materials using the principles, of course, of condensed matter physics, going all the way down to, this is the example of the hydrogen atom, which is the easiest to look at, where you have spin orbit coupling. So let me stop there, take questions, Mahalakshmi and Professor Amuda. I hope you have gotten the excitement of this new era of computing. Happy to take questions. Absolutely, Amuda, no problem. It's a pleasure. Yeah, yeah. Yeah, yeah. Happy to answer the question. Yeah. Yeah, yeah. Yeah. Yes, Ajomia, please, you had your hands up. Can't hear you. Yeah, that's a great question. I probably we hit you very hard with a lot of quantum mechanics and this and that. But what I wanted to convey is that you can go all the way from your physics class, which you start in your undergraduate, and then of course you go to the graduate, and then hopefully you will go do research. The easiest thing would be to start to do research. Whether you do research at IIT Madras or you can go to. I used to do research at Vivekananda College when we were in undergrad. I just work with some professors. You could go to IIT Madras or ISC Bangalore. They all have fantastic capability. If you're interested, I can set you up with Prasad. Two of my postdocs are now big professors in Bangalore. Or you should start to if you're interested really doing a PhD, start to apply to places. And go crazy. Go have fun doing research. A lot of this is a good question. A lot of Indian students want to go get a master's and then be done. There are two different things. If you do a master's, generally you don't do much research. Master's is a year and a half, maybe 2-year program. You don't do much research. You just take classes, do a small project, and boom, you're done. But if you do a PhD, that takes longer, typically about 5 years, but you're actually doing independent research. And when you will publish papers, science, nature, whatever, then you go into a different position. For example, you cannot become, all your faculty have PhDs, right? So if they only do a master's, they're not going to become a professor. So your pathways for careers are very different. Like in the United States, I'm sure India also doesn't have enough women faculty. So I encourage all of you all to go get a degree, PhD, go become professors. India needs a lot more women faculty members. So that truly depends on what you want out of life. Whether you want to do great research or just go get a job in a company, all things are available. Yes, that's right. That's right. That's a great question. Again, I'm an experimentalist, right? So, my answer is going to be, oh, you got to do experiments. But I understand doing experiments is expensive. But, India has a lot of capabilities. My postdocs got what amazing amount, $5 million worth of startup package. So it's not an issue. It all depends on what. It's like music, right? I grew up listening to Carnatic music, but if you're North India, you go listen to Hindustani music, right? There's nothing right or wrong. It's just what you want. They give you different perspectives. If you're doing computational physics, it's not wrong. You can do ab initio. Some of my best friends are theorists who do ab initio calculations. That's good too. It's cheaper because you don't have to buy expensive stainless steel and stuff. But you do other things with life. I think there's a lot of people who great theorists in India, especially in Bangalore and in Kolkata, some amazing theory folks. All depends on what you want out of life.
Good morning, sir. I have one question now.
Yeah,
Uh, yes, sir. It's RG Vaidya. So
Yeah,
usually in dealing with the electronics circuit, we usually take into account of the speed of the electron to be in the non-relativistic corrections.
correct.
Usually that is a non-relativistic approach. It is developed or it is accepted by all the research community.
Mhm.
Suppose in that case, if we take the relativistic corrections, does it add any new degree of the freedom for the electronics which we are going to see or not?
Yeah, that's a great question. Uh, uh, um, Typically, the speed of the electron, right, and the standard Drude model, that it's nothing close to speed of light. So even if you do relativistic correction, it's not a big deal. But
Because
when you,
nowadays,
when you
in the 2D materials or in the quantum levels, at the
that's right.
lower dimensional
Yeah,
levels, they are increasing the speed considerably.
yeah, exactly. Also, you have spin orbit coupling, which intrinsically is
Yes,
a quantum mechanical effect, and so
yes, sir.
that
Yes.
can change everything. It's a great point that you made. That's right.
Thank you, sir.
Yeah. Thank you. No problem. Most welcome. Yeah, yeah. Be well. Yeah. See ya. Bye. Good night. Guys.
Yes, yes. Thank you. Good morning. I do not know how to share because I'm not familiar with the Google Meet. Okay, thank you. How to share, Prof? How to share? Sorry, I do not know how to. Can I forward to you? Sorry. Okay, thank you very much for the kind introduction. Yes. Sorry, Prof. Okay. Is it okay? Okay. Is it okay, Prof? Not mail. WhatsApp. Uh, sorry. Is it okay? So, okay, I will email the Dr. John. So email to Dr. John. Dr. John. Sorry. Is it you, Dr. A.B. John Bejulia? Okay. Sorry. I'm so sorry. I think. Okay. Sorry. Okay. Thank you very much. Okay. Let's start. Okay. Can I start? Okay. Okay. Good morning to everyone. First of all, I would like to thank. I'm very grateful, especially to Prof. Durga Lakshmi, through my friend Prof. Saravana Rajendran, who's one of the committee of this conference also. And also, I would like to thank to Doctor who always communicating via email, Dr. A.B. John Vejula. So I'm very honored to be here to share.
Thank you so much, ma'am. It's a pleasure.
Woman. I think men. Okay, woman. Thank you. I would like to share our latest research, okay, about the fibrous silica-based catalyst for methane dry reforming. Okay, I'm Aisha. If there's our address. Okay, Center of Hydrogen Energy, Institute of Future Energy. Faculty, I also belong to Faculty of Chemical and Energy Engineering from University Technology Malaysia, UTM Johor Bahru, the South Malaysia, Peninsula of Malaysia. Okay, that is my email, and also you can see a little bit of about me from my website. Okay, if you can, okay, thank you. Thank you. Sorry. Okay, before we start, let's go for the introduction. Why we want to go for the hydrogen? Okay, as you know, all over the world now is talking about net zero by 2050. Okay, this is the aim or the goal of reducing greenhouse gases. Not yet. Proud, not yet, proud. The previous one. The previous slide, please. Okay. And also CO2 emission to prevent global warming. I think all knows about this. There are three main routes to decarbonization. The first one is reducing demand for carbon-intensive products and services, which is come from potential reduction of CO2 emission, come from majority from heavy industry, and also I cannot see heavy duty transport. Okay, and then the second one by improving energy efficiency, and then the third one by deploying decarbonization technologies across all sectors, including electricity, biomass, carbon capture, and also the main one is hydrogen. Okay, and next please. Okay, I share a little bit about the US primary energy consumption by energy source 2021, reported last year, 2022. This is the distribution of the energy consumption. As you can see, the renewable energy become 12% of total of the energy consumption in the US, which mainly come from the wind, and then biofuel, biomass, and also wood, and then go for the hydro and also the solar. Okay, next please. And this is the US energy consumption by major source from year 1776 to 2021. If you can see from the purple color from wood transform to the gray color, which is coal, and then until now the red one, the petroleum, and then also the become decrease, then to increase the hydroelectric. And also you can see the nuclear and also the green one, other renewable energy become the major one. Next please. Okay, this is the evolution of installed capacity by fuel in Germany. Okay, we can see two colors. You can see this is from 2002, year 2002 to 2018. We can see the blue color become decreased to increase the green color, which is the renewable energy. And Germany target in 2050, if you can see the right side, they want to decrease, target to decrease the GHG emission to 80 to 95. And then also the use of renewable energy, they target to use 60% for the energy consumption, and also for the power consumption, they targeting to 80%. Next, please. Then this is the net generation capacity addition. I pick up biofuel in India. Okay, this is from 2011 to 2017. You can see the black color coal become decreased, and the solar, the yellow one, increase at 2017. And these all data used showing that the transformation from the fossil fuel to the renewable energy. Okay, next please. Next please. Okay, this is the evolution of renewable energy capacity by source in Southeast Asia. Okay, renewable installed capacity increased more than triple from 2000 to 2020, from 20 gigawatt to 87 gigawatt. We can see the light blue color, the hydro increase, and also the solar increase, as well as the bioenergy. Okay, next please. So go back to the first my first slide. I want to talk about the no, it's okay. Same slide with the first slide. Okay, I want this is from here. I go for the hydrogen. Okay, next slide, please. Why everyone want to produce hydrogen? Because as in the previous slide, we want to reduce the greenhouse gases and CO2 emission to prevent the global warming. So, and we also know the depletion of fossil fuel stocks have to overcome, and then we try to go for the hydrogen. Next please. Okay, why we need hydrogen? Because hydrogen is the important one for the zero emission, and we can obtain the hydrogen from various methods. If we can see at the left side, there is various methods for the hydrogen production, including photoelectrochemical, water splitting, dry reforming of methane, bioconversion, gasification, and also geothermal energy. Okay, the hydrogen produced can be used for the petrochemical, fertilizers, heating vehicle, hydrogen vehicle, and also synthetic fuel. Okay, next please. Okay, this is also the hydrogen production system where we can get the hydrogen from various methods, from thermochemical, electrochemical, photoelectrochemical, biomass gasification, solar thermal, electrolysis, and also electrolysis. Next, please. Okay, this is hydrogen as a cleaner fuel. The breakdown of global hydrogen production by source in reported in 2019. Okay, if we can see, we can get the pure hydrogen majority from the methane, and also methane or coal. We can also get hydrogen, but in the form of syngas, CO plus hydrogen. And others is from coal also. We can get pure hydrogen, but mainly is from methane, okay, and or coal. Okay, next please. Okay, this is why we need the hydrogen, global hydrogen demand. Okay, mainly from 2020, 2025, and 2030. The main one, the hydrogen is used for the industrial, and then for the grid injection, and also for the refining, as well as power, and also the ammonia synthesis. Okay, next please. This is the color of hydrogen. Everyone talking about the color of the hydrogen. The color of the hydrogen is depends on the preparation method. of production method of the hydrogen. From the top one, we have brown or black hydrogen, which is from coal. We get from the hydrogen mixed with the CO2 that release to the atmosphere from the steam reforming or the gasification. That's why we call it as a black or brown hydrogen. And then if we and then go to the white is the atmosphere hydrogen. Then go for the gray. Gray similar to black, but this is from natural gas. Also, we can get from steam reforming, and also the CO2 is released. But if the CO2 is captured and stored, we call it as a blue hydrogen from the natural gas. And then the turquoise also from natural gas, but using pyrolysis method. Then we can get the hydrogen and also the carbon solid. And then the red, the purple is from the nuclear power by catalytic splitting or electrolysis, water splitting. We can get the hydrogen and also the oxygen. And then yellow is from solar power, electrolysis also. And then the green one, the last one is the renewable electricity, also from water, from electrolysis, just water. And then solar, okay, we can get the photoelectrochemical water splitting. Next, please. Okay, this is from the first slide. There is three main hydrogen production routes and colors. At the moment, if gray hydrogen, this is the hydrogen obtained from the reforming of coal or natural gas or biomethane, and the CO2 is released to the atmosphere. But if we capture the CO2 from the same sources, we can get the blue hydrogen. This is the target. We target the world target until 2030. Then after that, the green one. Okay, this is from use water, the renewable energy from water. And also from solar, okay, to get by photoelectrochemical water splitting method to get the hydrogen and then clean oxygen. And next, please. That is just the use of the hydrogen. Okay, I share also. This is the application of the hydrogen vehicles. I think everyone knows about this. The Toyota Mirai from Japan. Already launched in 2014, and then the hydrogen train, world first hydrogen train, launched in French, used in Germany also, Coradia Island at 2021. And then I just pick up yesterday, India also, the first hydrogen train will launch in December this year, 2023. So India is very advanced, wait. Then the Japan will launch in 2030. So this is all the world targeting to use the hydrogen vehicles. Okay, next please. Next please. Okay, go back to the topics, our topics, the syngas production. Okay, there is 4 methods. If we can list, there's 4 possible option that, to produce the syngas from natural gas. Okay, one is the partial oxidation of methane, then autothermal reforming of methane, steam reforming of methane, dry reforming of methane. Okay, each method have their advantage and disadvantage. For example, partial oxidation of methane. Partial mean half of oxygen. Okay, from methane we can get the CO and two hydrogen, and also in parallel we can get a side product, CO2 and also water. Okay, the disadvantage of this method and risk of explosion, then difficult to adjust the hydrogen CO ratio, and also requires pure oxygen. Then for the autothermal reforming of methane, extensive energy input, small scale hydrogen production, and also concurrent control of steam, oxygen, and CO2. Then for the steam reforming of methane, CH4 plus hydrogen could produce 3 mole of hydrogen and CO. But this method is required harsh condition, which is high pressure and also strong endothermic reaction. Then need to adjust the H2 CO ratio. Then the last one, what the topic of this speech today is about the dry reforming of methane. The advantage is utilization of two most disturbing greenhouse gases, which is methane and CO2. And then the product ratio, hydrogen and CO is 1. And then, but still, the disadvantage is still is excessive cooking and also highly endothermic, and also poor activity at low temperature. So require high temperature. So we are looking for the advanced catalyst to reduce the temperature. Next, please. Okay, this is the application of syngas. Why we want to produce the syngas, and why different ratio, different method will give different H2CO ratio, and then we can use in different application. For example, maybe for our dry reforming of methane, for the 1:1 ratio, maybe good for the ethanol production. And then maybe 2:1 from the partial oxidation of methane, maybe good for the Fischer-Tropsch reaction for the production of gasoline, naphtha. And then for the 3:1 from the steam reforming of methane, maybe good for the boiler for steam and power, gas turbine, and so on. Next, please. Okay, this is the summary of the methane conversion to syngas from the steam reforming, partial reforming, or partial oxidation of methane, and also dry reforming. Okay, from methane for the steam reforming, no oxygen, just methane and water to produce, but the ratio for the is higher. The ratio for the syngas is higher, 3:1, the product. And then partial oxidation of methane is 2:1, and dry reforming is 1:1. Okay, next, please. Okay, this is the advantage and disadvantage or weaknesses of the each 3 methods. So if we can see the steam reforming of methane, there is a large industrial use in a large scale generation, and then high efficiency without oxygen, high selectivity because 3:1 of hydrogen, and then but they need they produce high CO2 emission. And then 3 hydrogen to CO ratio for downstream processes. It's not so it's too high. And then for the endothermic nature and severe heat duty, the temperature we can see the 700 to 1000 is quite high. And then the POM, a high reactant conversion, the advantage, short residence time, rapidly and mildly exothermic reaction. But hotspot or hot zones formation on catalyst bed due to the exothermic nature, and also explosion is possible from methane and O2 mixture. Then for the DRM, the advantage is we use 2 greenhouse gases as a source. Then green process, we can call it as a green process, and also good for the production for the further use for the physiotrope. And then physiotrope relation, and then can carry out in moderate temperature, because from 650 to 850. Then the weaknesses, fast catalyst deactivation caused by the metal sintering and also carbonaceous deposit or coke. And then high cost of noble metals. Usually we use noble metals as a catalyst. Next, please. So this is, maybe we cannot see, difficult to see. This is our previous studies. Okay, it's okay. Can we go next, because we cannot see? Okay, okay. This is the history from when we use our fibrous silica catalyst. This is inspired by inspired by the discovery of KCC1 by the Prof. Polistiwa. What is KCC1? KCC1 is the KAUS Catalysis Center. KAUS is the King Abdullah University, Science and Technology in Saudi Arabia. At that time, Prof. Polistiwa was there. Okay. Now, when I search Polistiwa, now is in India, I think in Tata. Okay, I'm very grateful to this professor, because from the KCC1 we developed many catalysts for our lab. Okay, what is KCC1? If you can see, KCC1 is like a rambutan or chestnut. Okay, the size is not so small, still big. Okay, if you can see, maybe 300 to 400 nanometer, or maybe more, 500 to 600 nanometer. But the surface area is quite high, because you can see the fibrous shape of the KCC1 is very useful for any, I can say, for any reaction. Okay, for any application. Okay. They published in Ajiwante in 2010. From here, we developed our catalyst. Next, please. Before that, we try to use, if we can see from the left, the KCC1, the application, the isomerization is was done by the Polistiwa group in 2010. And then we try also to use the KCC1 load with metals, for example, nickels. We successfully use the KCC1 on methanation, CO2 methanation in 2016. And then 2019, my student also tried to use the KCC1 load with nickel also, and successfully used in methane dry reforming. And then 2020, we tried to modify actually the KCC1 is all silica. So we tried to modify the silica inside silica with other seeds, with other material. We successfully synthesized and replace the silica inside with the zeolites, for example, modernite, ZSM5, zeolite beta, and HY, and so on. But until now, we just cannot replace the outside silica. Okay, if we can replace the outside silica with other metals or other materials, it will be more useful. So 2020, we also go for the CO2 methanation, and 2021 for the methane dry reforming. We try to use to replace the zeolite with the alumina, and we successfully synthesize the fibrous silica alumina. And then now we are doing for the fibrous silica titania. So This is only for the gas ration, but we also use these fibrous silica metals catalyst for photodegradation of pollutants for wastewater treatment, and also for water splitting, PEC, photoelectrochemical water splitting, and also we still try to replace the inside with many metals. Okay, that is the history or chronology of our fibrous silica metal oxide development. Next, please. Okay, this is performance of related catalyst. We use the same method to produce the nickel KCC loaded on KCC. We vary we will see later. We vary the preparation method. 1P is belong to one pot. IM is impregnation, and then we compare with the nickel loaded on commercial silica. Then you can see the surface area is about, KCC is about 500 to 700 meter square per G surface area. And then we use for the DRM. And also we also use we also use other catalysts, fiber silica alumina, fiber silica modernite, fiber silica ZSM5 for the CO2 methanation. You can, if someone want to see in details, maybe you can check our publication from our website. That as you can see in the reference. Okay, next please. Next please. Okay, this is the first one. What I said, the DRM over nickel on KCC1, done by my student from Nigeria, Nigerian, Abdul Rashid now is lecturer in Nigerian. Rashid synthesized two different methods, the catalyst. One is by one pot, and then you can see the left one, and then the center one is by impregnation, and then compact with the nickel silica, commercial silica. We can see the methane conversion and CO2 conversion. Maybe we can see that there's no significant difference, but still the nickel KCC 1P still the top one, and then not on the performance of the methane and CO2 conversion, but on the stability. We can, if you can see, the stability is very high for the Ni KCC 1P compared to the nickel KCC 1M, impregnation IM. Okay. Okay, the graph show here, the bar graph. This is the hydrogen to CO ratio. We can get almost 1.4. And then why this is so different in the catalytic stability? This is because of the, if you can see the right one, the basicity. This is the difference in the basicity of each catalyst. You can see the nickel KCC 1P, the basicity is similar to the nickel KCC 1M, but the nickel commercial silica commercial is too low. That's why maybe different in stability. But the higher there's from this study, the higher the stability, the higher the basicity, resulted in the higher stability of the reaction. Okay, next, please. Okay, this is also DRM carried out over nickel, lanthanum. Abdul Rashid also nickel, lanthanum, KCC. Rashid at lanthanum on the nickel KCC, and you can see the the methane and also CO2 conversion increase, and also the stability increase more. This is the highest one in Abdurrashid study for the nickel on KCC1. Okay, but the basicity, if you can see the gray one, the best catalyst is the nickel lanthanum KCC1, but the basicity is not the highest one. The basicity, the highest one is the without nickel. So from these two slides, from this study, we can see that the highest basicity not always good. The appropriate basicity is the best one for each catalyst, for each reaction. That's what I can say. Next, please. And this is also DRM, but over done carried out on tantalum loaded on nickel ZSM5 zeolite catalyst, done by Hambali, also Nigerian. My student reported in 2021. So Hambali add tantalum. If you can see from the graphical abstract at the center, and also the bar graph. Okay, the bar graph showing the saturation of the in parallel with the DRM. Okay, there is methane cracking and also bonded reaction. When we add the tantalum, we can suppress the methane cracking. So if you can see, the y-axis is the carbon deposited. Okay, we can see the 7 nickel, the second one from the left, the 7 nickel, 3 tantalum is the last one. So this is the best catalyst for in this study. Okay, less methane cracking and also bonded reaction. Okay, if you can see the below graph below the A, B, and C. Okay, the green one is the nickel tantalum with the that is the for the 7 nickel 3 tantalum give the best result. And then in CO2 conversion, CH4 conversion, and also almost 1 H2 to CO ratio. Okay, next please. Okay, this is the last one. This is the DRM over nickel fiber silica alumina. Okay, we can see the high stability of that catalyst compared to the nickel silica alumina from commercial silica alumina. Okay, what I can say, our fiber silica catalyst is very good in this DRM and also as well as other reaction. Okay, next please. This is done by Ogi. Okay, that's all for today. I would like to thanks to all of my students because of them. I'm here now. Okay, next please. I touch a little bit about next please. Is it all? Next. Is it all? Hello? Is it all?
Yes.
I think I have an other slide. Hello?
Yes, ma'am. 1 second.
Huh? Hello? Is it all, Prof? Hello?
Ma'am, please, 1 second.
Kindly stay online, ma'am. Checking. Kindly stay online. We are checking.
I cannot hear you. Hello? Hello?
Once again, ma'am, please.
Hello, hello, hello. Okay, I want to touch just a little bit about our center. Okay, this is okay. As you can see from my first slide, okay, I come from Center of Hydrogen Energy. Actually, we have 3 centers under my institute, what we call it Institute of Future Energy. That is Center of Hydrogen Energy, and then Center of Electrical Energy System, and also Center of Ocean Thermal Energy Center. Next, please. Then we are doing. Can you enlarge slideshow? I cannot see. Sorry. I'm just looking for the collaboration from others. Or okay. Okay. For the center, what we are doing now is we're doing from the hydrogen, because Center of Hydrogen, so we are doing from the production of hydrogen, storage, utilization, safety, risk assessment, and also simulation. So we have many experts from that particular area. So we are looking for collaboration. We are looking for students, for postdoc, and research fellow, and so on. Next, please. Next. Again, let's collaborate for our sustainable future. And then next. Thank you. Thank you. That's our address. You can search utm.my, okay, for our university. Thank you. Thank you very much. Thank you, Prof. Thank you, Mr. Chairman. Thank you. Okay. Thank you. Thank you. So can I leave now? Okay. Thank you. Thank you. Thank you. Thank you. Thank you very much.
Good morning, Dr. Durgalakshmi. Am I audible? Yeah, just give me a minute. Yes, I'm ready actually. 1 minute, let me share my screen.
So now we have our
Yeah, good morning. Thank you, madam. Thank you very much. My slide is visible to you all? Yeah, thank you. Thank you, and very good morning to all the faculty members, the organizing committee, and the students as well. So I'm very happy to share my research findings with you all. And as you might be already knowing that the title of my presentation is Nano-Dimensional Thin Films for Optoelectronic and Energy Harvesting Devices. So in this particular talk, I will be dealing about mostly thin films and their applications. So my outline of my talk will be like this. So first I will try to introduce you some of the basics of thin films, how one can deposit thin films, and what are the basic characterization that is necessary to characterize the thin films. And secondly, I will try to give you an overview of what are alternative transparent conducting electrode systems, and why do we need it? Why do we need an alternative system as of now? The need I will try to focus here. Then I will go for an oxide system, so which is nothing but tantalum doped tin oxide system as an alternative transparent conducting oxide, how it can be effectively made, and how it can be effectively characterized, and how it can be effectively used in at least one of an optoelectronic device application. And finally, I will discuss about gold, silver, gold, or gold, platinum, gold tri-layers based upon metallic systems, how to fabricate them and how to characterize them, especially for their bending twisting properties, and then how one can utilize them in more than one type of optoelectronic devices. Okay, right. So in all these topics, I will try to scale down my presentation so that it will be more comprehensible for the listeners. Right. So to start with, let me go to the introduction to thin films. So here, as you see here in this particular picture, I have portrayed several of the real-time components and utilization of thin films in our day-to-day life. So as you see here, in this spectacles or in this particular expensive camera lens, you have some kind of coating there. So that's called as anti-reflection coating. So most of your cameras or even nowadays mobile phones will have anti-reflection coatings are there. Okay, so wherein you can eliminate the glare from outside light and making your visibility very clear. So that's what is called as an anti-reflection coating. So which is going to suppress the glare that is formed on the surface of your lenses, right? So, or if you're going to take a package of a lace chip, say for example here, you will see that the inner part is coated with some kind of aluminum foil will be there. So this is not a very thin film. In fact, this is a slightly thicker film. But still, the purpose here is it will not allow the moisture from external atmosphere to penetrate into the the packet, so that the contents of your your package will be kept very fresh. So likewise, you will have anti-reflection coating in the case of headlamps, and then you will have a hard diamond-like coatings on the drill bit so that it can function for quite long time. So not only that, if you even take a SIM card, all these SIM cards will have a very thin layer of gold coated over it, so that with respect to long-term usage, it will not have any rust formation, because that gold is a noble metal. So even if you heat it at room temperature, to a higher melting point, you will see that in room ambient atmosphere also it doesn't get oxidized there. So that's why you use a thin layer. So again, thinking about this one, you cannot use a thick coating of gold there, because then no company can give you free SIM cards there. So why they are able to give there? Because we are coating this gold as a very thin layer. So you will see that the cost reduction is there. Still, it functions. The necessity is actually met out there. So like high conductivity and then low oxidation kind of things. So not only that, even if you see the LEDs available in the market, or flexible solar cells, or even your touchscreen mobile phones and laptops or tabs, they all have thin film as a integral part. So we may not be aware of that, but definitely it has one component or several components as a thin film. Say to mention some more, you can see here defrosting windows in airplanes. Even say in your four-wheelers, in your cars, you will see that a very thin line will be there at the back windshield. So those are nothing but a very thin conducting wire where you can apply a small voltage to defrost the moisture or the frost that is formed on the surface of the glass, so that you can have a clear view. So nowadays those lines are not used, because instead of that we use a completely transparent material which can conduct, and then it can also heat it. So you can apply a small voltage, you will see that it will slightly get heated up, and then you can melt off the snow formation or mist form that is settled on the surface of your windscreens. So that will be giving you a clear view of the road while you are driving in your winter season. Okay, so that these are some of the real-time applications. But apart from this, there are a lot number of intense applications. Say for example, your IC packaging. So integrated circuits you are forming, they will have different types of materials. Not only there, even in silicon photonics, we will have thin layers of different materials, wherein you can apply a voltage or you can apply a current, a kind of electro-optic property modification can also be done for materials when they are fabricated in the form of thin films. So thin films inevitably forms a component in several of the day-to-day components which we are using in our real life. Right, now let us see that this is another simple example wherein a thin layer of material coated as an anti-reflection coating. So you can see that if I'm going to have a lens system like this, if I'm going to have a glare formed on the surface, a glare is nothing but an interference maxima which is formed on the surface due to the external light falling on the lens. Which means that when I'm going to view through this lens, it's going to be a kind of bright spot on the picture or even on our pupil. So which is going to obstruct the real-time light real view of the image. So in this case, we have to nullify this maxima which is formed on the surface. So to do this one, what generally people do is they'll give a thin film coating on the surface of your lens. And the thickness of this film has to be manipulated such that it will give rise to a destructive interference on the surface. So when light is reflected from the surface of your coating and surface of your lens, they will have a path difference. So this path difference is actually manipulated based on the thickness of your thin film, so that it leads rays to a destructive interference on the surface, so making the light to enter into the lens and then fall onto your photographic plate or onto your eyes, so that the glare is actually eliminated there. So you can see the pictures of a lady wearing a lens without an anti-reflection coating, wherein you can see that particular light image glare is there. So when a coating is given there, you can see that that light is actually eliminated, and you will be able to see through the lens very properly. Right. This is some of the example. Now let us come to what are thin films actually. So thin films are layers of material which are deposited or coated over another material by using different kinds of techniques. So it may be a chemical technique or it may be a physical kind of technique you can utilize, but you can coat a thin layer of material over another material, which is called as a substrate. So in fact, in general terminology, the thickness of the material which you are coating should be less than 1 micrometer in general. Okay, but actually 1 micrometer is, in fact, is really thick. So just for the sake of definition, we'll put them as 1 micrometer. But actually, thickness is a property of the film which asymptotically reaches that of the bulk is reasonably characterized as thick. So in other words, we'll see that when I can call a material as a thin film. So as long as the thickness is going to introduce a different property to that material compared to its thicker form, you can call that term, that limit, as a thin film limit. Okay. So typically, if you see that films can vary starting from say 10 angstrom to even 0.001 micrometer or to 1 micrometer thickness, you can term as a thin film. So again, this depends upon what kind of material and what kind of application you are looking into. This definition of the thinness of the film will slightly vary. Right. So you can see here this particular picture given over here. This green color is actually the substrate. Over the substrate, you are going to coat a very thin layer of material of your interest. That is what is called as a thin film. So in general, you will see that you need a substrate for us to coat the film. But there are some exceptions. Let's say, for example, you can make a graphene layer, which is really thin in form. You can make it without a substrate also. So you can do some chemical process. You can eliminate the the substrate by some kind of sacrificial template, and then you can still have a very thin layer of the graphene floating on a fluid. That is possible. But once again, handling them will be very difficult. So mostly, we need a substrate for coating the thin film to put it into effective usage. So as you see here, this classification, say 1 mm, I can call it as a sheet or a plate. And if the thickness is around 10 micrometer to 100 micrometer, we call that as a thick film. If it is around 1 micrometer, we call it as a foil. And then less than 1 micrometer, you can see this entire region, you can call it as a thin film. Okay. So depending upon what is your necessity and application, you can make a film of particular thickness. So not only that, so why do we need a thin film? So thin films are, highly sorted out because they are very compact in nature. Their performance is really good compared to their bulk counterpart, and they are highly reliable, low cost of production. Especially when you go for a mass production, its cost per piece will come down, and it's going to have a low package weight. Okay. So above all, you will see that they have novel properties which are very different from their bulk counterpart. Say, for example, if you are going to have a material with a certain electrical and optical properties, if you start depositing this material as a thin film, you will see that these electrical and optical properties may be significantly different when you reduce the thickness. So that's the limit where we call that as a thin film, and that's why we use a thin film. So in the due course of this talk, we'll try to understand what is the effect of film thickness on the electrical and optical properties also. Right. Now let us try to understand how these thin films are formed in general. So whether you can have a physical vapor deposition technique or a chemical vapor deposition technique, whatever it may be, how these films are in general formed. So let us take these 3 steps here. So the first step is you have to create the material in vapor form. So whether you adapt a chemical or a physical technique, whatever it may be, first you have to create the material of your interest in the form of vapors. And then they have to be effectively transported to the surface of the substrate. And then I have to allow them to grow as a thin film. So these are the three fundamental steps which are involved in the formation of a thin film. So let us try to see this picture really. Say this yellow color region here is actually the substrate. So this kind of gray color, spheres are actually the material or the vapors which are coming onto the substrate. So as you see here, so these individual atoms or molecules, they arrive to the substrate, and then with respect to the substrate temperature, which you will be giving intentionally, you will see that these atoms or molecules, they try to group into a small a group which is called as a doublet formation. And then with respect to further incoming species and also the temperature, you will see that these doublets will grow into bigger size, and that we call it as a nucleation. Still you see that several parts of the substrate are not coated yet, and still there is a formation of nucleation is happening there. Now with respect to time, you will see that these nucleates which are formed will grow in size. So they grow in size. Not only that, over a period of time, they also merge with each other, which we call it as a coalescence. So now if you keep depositing for further a good amount of time, you will see that more number of nucleates will form, and then they will try to grow in size, and then they will try to merge with each other. Finally, they cover the entire surface of your substrate. So now you see here, there is no yellow color substrate seen over there, because the surface is entirely covered by the material of our interest. Okay? So this is how a thin film is actually formed. Now we can categorize this thin film formation into different processes. How these films are actually formed when I try to do a chemical process or when I do a physical process. What are the competing mechanisms that will happen there, and which mechanism I'm supposed to allow to grow further, or which mechanism I have to suppress it to have an effective film formation. So this is very important. Say for example, if I do an evaporation of a material by chemical or a physical vapor technique, you will see that the atoms or molecules will try to come and fall onto the surface of the substrate. So when they come to fall, you will see that several things can happen there. So these atoms or molecules, they can simply condense on the surface without much bond formation, or they can just adsorb onto the surface, or if the substrate temperature is going to be larger, you will see that they can once again re-evaporate, and then they can go outside the substrate itself. Or if the conditions are very much favorable, you will see that they try to nucleate on the surface, and then they try to grow in size, and then they will try to coalesce with each other, try to do a surface coverage. Or if the temperature is much more larger, or if the evaporated species is having some kind of chemical affinity to the substrate, you will see that they will have some kind of interaction, and then they can even enter into the substrate. Okay, so if they try to enter into the substrate, many times it's not preferable, because we want the surface to be coated only. We don't want it to dope it by entering the evaporated species into the substrate. So that's what we don't need. So in this case, if you see that if I want to really have a good thin film, so I don't want to have re-evaporation, and I don't want to have interdiffusion. Okay, so what I want to do is I want to have a surface diffusion or mobility of the atoms on the surface, and then a nucleation should happen over there, so that effective coverage of the surface will take place. So all other mechanism, I don't want it here. Again, a simple adsorption will not be very much helpful, because after the deposition is done, this material will get removed from the surface if you have a simple adsorption. So they should have a proper nucleation and bond formation onto the surface to make a two-dimensional surface coverage. Right. Now let us see a cross-sectional view of how this thin film is formed, starting from the nucleation stage. So if you see this picture here, this part is your substrate, and then these are all the evaporated species which is coming towards the substrate. So when they just fall onto the substrate here, you will see that they form into a slightly bigger nucleates will be forming over here. Okay, and then with respect to time, you will see that this nucleation which is formed will try to grow in size as independent islands. You can see here there are independent islands, but still there are some regions where they have not yet completely wetted or covered the surface of your substrate. With respect to further deposition, you will see that neighboring islands which are bigger in size, they try to merge or coalesce with each other. So in this case, you will see that with respect to time, more surface coverage is actually happening over there. Now this is called as coalescence stage 1 and stage 2. So in stage 2, you will see that more number of islands are formed, and more of them are actually merged with each other. And then only a small gap is left out between them, which looks like a channel. So this is called as a channel growth. So with respect to further deposition, you will see that these channels are also completely covered with your material. And finally, I'm having a complete coverage on the surface. So this is my substrate surface, and this is my material of particular thickness T. And you see that there is no uncoated substrate left out over there, like a channel. But again, you see that there is some kind of interface is there between the grains. So because it is forming a film by way of island growth method, obviously there will be a lot number of grains and grain boundaries will be there. So this we call it as a polycrystalline thin film forming on a surface. Right. Now we can try to really classify this thin film growth, into three different modes of growth. Say, for example, if you choose a chemical technique or you choose a physical vapor deposition technique, what differences it will have on the quality of the thin film is very important. Right. So if you see here, the first one is an island growth mode, or called as a Walmer-Weber growth mode. So here you will see that the incoming species will form small nucleates, and then they grow into bigger islands like this, and then these islands will merge with each other. So because of this one, you will have a lot of grain boundaries will be there. This is usually will happen in some kind of technique, like say for example thermal evaporation technique. It will happen. Not only that, if you are going to modify the growth conditions, you can even achieve a layer by layer growth method, otherwise called as a Van der Merwe growth method. So here you can see that there will be coverage of the surface of the substrate first, then only it forms next layer. So whereas in the previous case, before coverage itself, I was able to form second layer, third layer. So it forms a kind of island without completely covering the surface of the substrate. But in layer by layer growth method, that will not happen. As you see here, first layer will be completed, then second layer, then third layer, then fourth layer. So you will see that there is a very systematic formation of the layers, and then the film is formed. Now here, this will be of very high quality. Almost the grain boundaries will be very, very minimal. And third one is called as a mixed growth mode, or Stansky-Krastenov growth mode, wherein you are going to have initially there may be a layer by layer growth methodology, but after a few layers, you will see that I'm going to form an island over there. Okay, so there will be a different island formation will be there on the surface. So this will be having a film quality in between these two. So usually if it is an island growth mode, you will see that the quality of the film will not be very good. Mostly it is polycrystalline. Whereas if you are going to have a layer by layer growth mode, you will have a very good quality. And the quality of this mixed growth mode will be in between these two. So this all depends upon what are the deposition parameters you are going to fix and what is the deposition technique you are going to adapt. That will dictate the type of growth mode. Right. Now coming to the factors that are going to influence the thin film. Say for example, I am going to grow a thin film by chemical or a physical vapor deposition. What are the general precautions or what are the general steps that I have to take care to end up in a good quality thin film? So first one is cleanliness of the substrate and the deposition chamber. Both should be highly clean. And then type of the substrate. What substrate I'm going to choose is also very important. If my substrate is a single crystal substrate, then the film which is grown over that will also have a good quality. If my substrate is damaged, it has a lot of defects or it's polycrystalline, the film which is grown over that will also replicate that one. So the quality may be, very poor there. So that is also given as a epitaxial or textured or polycrystalline. So your type of substrate and what is the lattice parameter of this substrate with respect to the film which you are trying to grow over there. Say for example, if you grow a cubic material on a cubic substrate, then the growth will be much bigger. Or if these two cubes have mismatch in their size, the substrate is very bigger, or if the material which you are growing is having a smaller, cube dimensions, you will see that there will be a mismatch. So that will be leading rise to a lot of stress and strain in the material which you are trying to grow over there. So likewise, substrate temperature, how much substrate temperature you are going to give. And then inert or reactive atmosphere which you are going to maintain in the deposition chamber is also very important. And what is the film adherence and what is the rate of deposition. So this rate of deposition is also very important, which dictates the quality of the film that is going to be formed on the surface of your substrate. Now coming to general steps of substrate cleaning. So whatever substrate you are going to buy from a company and to coat your film there, one has to take care that they should be cleaned very nicely. So though these thin film substrates are going to come in a nice package, it doesn't mean that the surface are very clean, because there will be having a natural carbon contamination, dust or moisture will be there due to the storage there. So we have to clean it. So first one has to use a mild detergent and then wash it for some time, maybe in an ultrasonicator, and then you can put it again by rinsing with a clean deionized water, because your water also should have should not have any kind of contaminants. Say commercial water on your taps will have a lot of fluorine, calcium, chlorine contents will be there. So I cannot use it, because those atoms or molecules in the water will again contaminate my film which I am trying to grow over there. So one has to use a completely deionized water. And then I can again clean with a mild dilute acid to remove any kind of grease or oil sticking to the surface. And then again I can clean once again with the deionized water. Maybe all these things can be done in an ultrasonication. Okay. So in an ultrasonic bath, you will see that it's going to create a lot number of bubbles at a faster rate. Okay, so they will create and then they will crack. So thereby inducing a high pressure, high temperature for a very fraction of a second. So that will help you to remove the dust particles from the crevices of the surface of your substrate. The surfaces of the substrate will look visibly very smooth, but if you put it under a microscope and see that, you are going to have a lot of wrinkles or crevices, mild cracks will be there. So all this oil and the grease will be sticking onto the surface of this particular crevices. So we have to remove them effectively. So that's why we are going for an ultrasonication. So later one can use an organic solvent to remove them completely. And you have to do all this process mostly in a dust-free room. And again, the surface has to be cleaned with a jet of inert atmosphere like nitrogen or argon. And then you can put it inside a chamber where you can create a plasma to once again clean the surface very thoroughly. So this substrate cleaning step is very important, especially say when you are going to make an integrated chip, okay, for your electronic purpose. You will see that you will be forming several diodes or transistors onto the surface of the substrate. So if the surface is not clean, the property of that particular component which you are forming at that particular junction will not function properly. So that's why the surface cleaning is going to be very, very important. And again, remember that these are only general steps. It will vary depending upon what is your substrate. So my substrate is a single crystal, I have to follow one procedure. If my substrate is a flexible one, is a low melting point, again I have to modify that one. Okay, so it all depends upon what is the choice of your substrate and your process. Right. So these are some of the steps which are shown over here. So I can take a glass substrate, put it in an ultrasonicator here, do a DI water for 10 minutes, clean it. Again, I can put a special soap solution. I cannot use Dettol. Dettol is a bit corrosive. Just only representation. So you can use a special mild detergent meant for this. I can clean it again, with DI water, then IPA or acid if necessary. Again with a DI water, again with an organic solvent. Then I can put it inside a plasma chamber, clean the surface. So once after cleaning is done, immediately you have to load it into the deposition chamber to start the deposition process. Because after cleaning, if you store it in an atmosphere for some time, again it starts gathering dust and molecules, dirt molecules from the surface or from the ambient atmosphere. So again, it's not going to be a clean surface. So always, once you are doing a plasma cleaning, immediately load it into the chamber. Or if your deposition chamber is going to have an in situ plasma cleaning system, that is well and good. So after loading also, just before starting your deposition, you can clean the surface once again. Right. Now, after cleaning the substrate, suppose you assume that you have deposited a thin film by some technique, say thermal evaporation or spray pyrolysis, which I will deal later. So what are the tests I'm supposed to do to test the quality of my thin film? So first one is tape test. So a tape test is going to tell you how good the film is actually sticking to the surface of your substrate. Because when I say a thin film, it has to be, sticking properly. So after deposition, if I wipe it with my hand, it should not come out, which means that, the adherence is very poor. So how to test this one? So this is only a qualitative test. It's not a quantitative test. So, or in other words, I can tell this as a semi-quantitative test. So you can take a very good quality Scotch tape like this, and then you can paste the tape on the surface of your film, and then you can pull it with a particular force. So if you do that, you will see that if the edge is, peeling off along with your tape, then the adherence is very poor. So again, it depends upon what is the the adhesiveness of the tape and what is the force with which you are pulling. So all these things are not constant. So that's why I told that it's only a qualitative test. It's not a very quantitative test. But we can make it into a semi-quantitative test. Say, for example, cross-cut test. So you can take the film after coating, a part of the film, and then you can use a sharp diamond tip, and then you can make a checked pattern like this. So after making a checked pattern like this, again now you put this tape onto the surface and start to remove it. So you see that some squares are removed here. Okay, and if you are going to do it continuously, more number of squares will be removed here. So this will be some kind of semi-quantitative test to study the adherence of the film onto the surface of the substrate. So if none of these squares are removed, which means that the adherence is going to be really good. So this is called as a tape test and a cross-cut tape test. And then I can go for a friction or a wear test or a ductility test or a hardness test. So all these things one can do it in a nano indenter machine. So there will have a very sharp tip of different shapes. I can do an abrasion on the surface of my film, and then at the nanoscale I can really test it. Whether the scratch is made on the surface or how much is it ductile. All those things I can do it using a nano indenter. Right now, likewise, you can do even a scratch test using the same nano indenter. And if the tip which you are going to put with a particular load is going to damage the surface, then from this I can calculate what is the adhesion strength of the thin film. So these are all very general characterization steps, one which has to follow during the optimization of the thin film formation. Likewise, coming to the thickness, next property is thickness, because I told you when I say a thin film, the first question is how thick is the film, because thickness is related to the property of the material. So one has to really determine what is the thickness of the film. So how to estimate the thickness of the film? By few techniques. So you can see here, what I can do is I can form a step edge. So for example, if I'm going to have a substrate and if I want to coat a film on the surface of the substrate, what I will do is one edge I will first mask with a sharp knife edge or even a tape I can put it before coating onto this particular substrate. Then I can coat the material with some process, chemical or physical vapor process. So once you coat it, you will see that the uncovered area will be grown with the film. And here, since I have covered the surface, you will see that the material will just fall onto the surface of my knife edge or a tape. So after you remove this one, you will see that my film will be looking like this. So film will be coated up to here, and there is no film here. So this edge is called as a step edge. Because the knife edge or the tape which I'm going to put here is very sharp, this will be having a step edge kind of shape. So what we can do is, again, a more clear picture is shown over here. So this is the film, this is the tape. So over that I have coated the film onto the substrate. The substrate is this one. Okay, this is my substrate here. So after coating this, you will see that the film is coated onto the substrate like this, and then I can remove this tape. So once I remove this tape, my surface will look like this. So this is my substrate here, and then I'm going to have a film here. But since I masked it here using a tape in this part, there is no film here, since I am physically removing that one. So I will have a step edge, something like this. Now what you do, you put a sharp cantilever tip from this substrate where it is uncoated, which will be positioned with a sensitive laser beam on the head of the cantilever. Then I can scribe it on the surface. So you will see that it will come here without any obstruction, and here it will just try to climb. So what is the height to which this cantilever is climbing is actually the film thickness. So you can see that this is called as a stylus profiler. So you can see you will have an in situ camera to position onto the region where you are going to make the measurement. So you can see here, this is a coated area, this is an uncoated area. So I can keep my tip somewhere here, and then I can scribe it across the step edge. So when I do this, you can see here, there is a step edge here. Okay, so the difference here after doing the baseline correction will give you the film thickness. So in this case, we have coated a yttrium barium copper oxide sample. The thickness was measured to be 96 nanometer, so very near to 100 nanometers. So this is called as stylus profiler technique. So again, remember that this technique is okay for hard kind of samples. The sample is a very soft material. You will see that this tip itself may damage the material. So one has to go for other techniques like an invisible technique where you will form an interference pattern, or you can go for an ellipsometric technique. Depending upon the refractive index, you can do a fitting, and then you can get the thickness of the film. Right. Now that is about the thickness. Then we have to measure what is the sheet resistance of the material. Okay, we have to see what is the resistance. So you know that Ohm's law, V equal to IR. From that you can calculate the resistivity of your system. Say for example, rho will be equals to RA by L. This is a standard formula which all of you will be knowing. But now this formula will not be working out here, because the problem here is I will have a substrate like this, and then I will have a thin film coating on the surface of the substrate, and then I'm going to keep 4 probes like this. So I will give a current here, and then I will measure the voltage drop between these 2 probes. That's how we do a linear 4-probe technique. But now the problem here is the spacing between the probe will be approximately 1 millimeter. 1 millimeter gap will be there. But the thickness of my material, say for example, it's 100 nanometer. Okay, so which means that the thickness is several orders less than the spacing between the probes. If this is the case, the path taken by the current will not be, fulfilling our standard formula, this rho equal to RA by L. It will not be obeying that. So we have to apply certain set of correction factors to that one. So that's why we call that as a sheet resistance, because our material is not a bulk 3-dimensional material. Okay, it's restricted along the z-axis. It will have only x and y-axis as a 2-dimensional material with a very, very small thickness. So I have to modify my sheet resistance R is equals to F into V by I. This is my formula for calculating my sheet resistance. So here you will see that if I'm going to choose the 2 outer probes 1 and 4 to apply a current and measure voltage across 2 and 3, you will see that the correction factor as per some theoretical simulation and considerations is 4.53. So my sheet resistance will be, I know what is the current I am applying. I am going to measure the voltage drop across this 2 probes. Then you put this constant correction factor there, and then you can calculate what is the sheet resistance. Okay. Not only that, I should always apply current between 1 and 4. In fact, I can choose any pair of probes there. Accordingly, my correction factor will be varying here, which is given in this particular table here. And then I can calculate what is my sheet resistance. And then the resistivity will be calculated by rho equal to my sheet resistance into film thickness. So this rho equal to RA by L will not be working out here. Okay, so I'm going to have only RS into T. This is called as a resistivity for my thin films. Right. Now, this is about basic characterization of a coated thin film. Now let us try to see where this transparent conducting electrodes are applicable. Say for example, if you have your mobile phones, over your mobile phones you have a lot number of layers and coatings are there. Say for example, if you buy an expensive mobile phone, the first thing which you do is you'll go for a scratch-proof card. Okay, so these scratch-proof cards are sold in the roadside markets, starting from 50 rupees even up to 300, 500 rupees. So it all varies because what kind of material you are coating on the surface of your scratch-proof card. Not only that, your actual screen, the touch screen which you are using, is also conducting there. So when you press it, yes, electrical signal is actually carried by the pressure of your finger. So which means that it should be conducting. At the same time, the light coming from the LEDs of your device should reach your eyes. So then only you can view a movie in your mobile phone. So that is the important thing. So now coming to the electromagnetic radiation, you will see that our visible range of radiation starts from around 400 nanometer up to around 700 nanometer. And you know that glass materials, semiconductors, insulators are all transparent or partially transparent depending upon the band gap. Okay, so glass is a transparent, but you know that glass is not conducting. Glass is an insulator; it will not conduct. But your mobile phones almost looks like a glass. So when I press the finger, I'm able to transmit an electrical signal. But how is it conducting? So what kind of metal is there actually? Though it looks like a glass, like a transparent glass medium, but it is not actually a glass. Okay, so there is some kind of coating given over there. So which should be both transparent at the same time conducting. Likewise, if you take a piece of copper or gold, these are metallic systems. So metallic systems, you know that they don't transmit visible light. Okay, but they are highly conducting because you know there is no band gap. In the case of your metallic system, band gap is not there. So they will have a valence band and conduction band overlapping with each other, and you will have a lot number of free electrons will be there. Whereas in the case of glass or semiconductors, you will see that there is a band gap. There is a valence band, and then there is a a conduction band will be there. So they are going to have a band gap between them. That's why they are not highly conducting like the case of metals. But the point here is, in all your mobile phones or your touchscreen or display devices, you need to have material which is going to have both these properties. Okay, so in fact, Maxwell equations does not permit it. Okay, so you cannot have a highly conducting glass medium because the band gap is so wide, it cannot conduct that much. At the same time, metals can be highly conducting, but it cannot allow the visible light to pass through it. So what we are supposed to do is we have to find a new class of materials which is going to have both these properties in the same lattice. So that is called as transparent conducting materials or transparent conducting electrodes. Let us see what are they. Okay, so as you see here, metals are highly conductive, but normally they don't transmit visible light. Whereas oxides or glass or semiconductors are highly transparent and they behave like insulators or semiconductors depending upon the band gap. Okay, so the challenge here is you have to achieve both these properties in the same host material. Okay, so what are the materials that are available to us? So the first one was cadmium oxide. It was identified in 1907 by Badeker. So this was having a very good performance. But again, the problem here is cadmium is highly toxic, so one cannot use it widely. Highly carcinogenic also. So that's why they dropped it. But there are some other set of materials which we can see in the due course. But what is the the requisite for such kind of transparent conducting oxide materials, which have high conductivity at the same time high transparency to the visible radiation? So the resistivity should be around 10⁻³ centimeter or lesser, and their average transmittance should be above 80%, and their carrier concentration should be around 10⁻20 per centimeter cube or higher, and band gap energy should be around 3 electron volt. Then only it can be transparent to the the visible range. So these are some of the conditions for a transparent conducting oxide. So what is the material that is available and where it is used? So if you see here, you are using such kind of materials already daily by each one of you, in the form of touchscreens, smart windows, LCD TVs, flexible organic LEDs, even in solar cells, it is already there as a component. Okay, so you see that the resistance which are shown here, 500 ohm, 400 ohm per square, or 5 ohm per square. So depending upon what is your application, the sheet resistance of your material can vary. So it's not like always it should be highly conducting. So depending upon your application, you can tune the sheet resistance of your material. And not only that, you can see that these materials should be environmentally stable. They should be very resistant to the aberrations. So for example, if you use your touch screen, they should not go bad within 1 month. You need to use it at least for 2 to 3 years. So the coating which is given on the surface should be hard coating. So with respect to your finger wiping, they should not get removed very easily. And they should have very good high work function and much compatible to the substrate and other device components which you are going to fabricate into that device, into that layer. Right. Now another example here is your touchscreen displays. So there are several number of coatings that are available here. So when you press your mobile phone, so you are going to have either resistive switching or capacitive switching. Both the things are available there. Say in this particular picture shown over here, I'm having a conducting layer at the bottom, another one on the top. So when I press it, you see that they make an electrical shock. This material is slightly deforming and that touches the bottom electrode, and thereby it gives a signal to your processor. So this is called as a resistive switching, where there is a physical deformation of the material to make an electrical contact. In other words, you can also make a device based upon capacitive switching. So wherein it will act like a capacitor. So one underlayer will be there, another top layer will be there. So if you touch it from the surface, its distance will get modified. So if distance modifies d, the capacitance will change. So most of your touchscreen devices nowadays, whatever you are using, are capacitive device only. So when you press your finger, the small finger pressure is actually really raised to a small deviation in the distance between the two electrodes. So when the distance between the two electrodes varies, obviously the capacitance varies. So the capacitance variation is actually given as a signal to your processor, and then you are able to pick up a call or watch a movie. Okay, that's how your capacitive switching actually works there. So in all these things, if you see that, you are going to have a material which is called as ITO, indium tin oxide. So if you see this here, I'm going to have an ITO coating number 6 here. An ITO coating is there. Apart from that, you have several other coatings also will be there in your mobile phones. Several layers of coating will be there. So just because of this thin film technology, all your mobile phones are very thin nowadays. So compared to 10 years back, if you see the mobile phones nowadays, they are very sleek and very thin and very lightweight. All these have been realized just because of the thin film coating technique developments or advancements in the thin film coating technology. Right. Coming to the actual material which you are using in the market is indium tin oxide. So which is nothing but 90% of indium oxide and then 10% of tin oxide. It is an alloy. Okay, it's an alloy, not a dopant. It's an alloy because the ratio here is 10%. They mix, nice, and then they make an alloy. So here, this is a degenerate semiconductor. So wherein you are going to have a lot number of free carriers given by tin into your indium oxide lattice. So you will have a valence band and conduction band, but already all your valence band is completely filled, and then the free carriers, already have entered into the conduction band. So by applying a small potential, these conduction band electrons can move freely, and then they can lead raise to a conductivity. So this is called as indium tin oxide. Okay. Not only that, you see their band gap. They have a sufficient band gap also. So the incoming visible radiation can easily pass through your material. So this is going to be highly transparent and also highly conducting. This is called as indium tin oxide. In fact, in all your cell phones and display techniques, this ITO layer is actually formed, inevitably. They will have default, they are going to have it. But now this material is performing really good. But now what is the problem here? The problem here is, availability. The material which is going to be available here is very, very, less in quantity in the Earth's crust. And you know that what is the need for this display technology in, current day market. So everyone, has a mobile phone, and, every month or every week, people are releasing new models and, new techniques in your mobile phone. So you always have an, intention to change your mobile phone at least every 1 year like that. So the demand is very huge. Okay. So there is a high need for indium tin oxide layers. But the problem here is availability of indium is very limited. That's why you have to go for an alternative technique. So let us see that nearly 8 to 10% of indium tin oxide is only available in the Earth's crust. And the recyclability of this, these coated ITO layers are very, very limited. Even if you try to do that by collecting the old mobile phones, the process of recycling is going to be very toxic. You have to use, very toxic chemicals to etch out this indium. And even if you do that, the quantity which you are going to reprocess or, recycle is going to be very, very limited and very expensive and very, going to be, hazardous process there. So that's why, we cannot recycle this indium tin oxide very frequently. And you see this projection which is given here. In 2017, the ITO alternatives are very limited. Mostly ITO in red color was used frequently. But they projected that in 2026 or 2027, the alternatives will be, very much like 50%, 40 to 50% as that of indium tin oxide. Because, there is a, very huge demand in the market. So that's why people have to explore alternative materials for this indium tin oxide. We cannot keep on using this indium because, indium is also very much limited only in certain parts of the countries only. It's not available everywhere. It's, say, for example, in China, Chile kind of countries only hold a huge deposits of indium. So we have to go for alternative materials. So what are the alternative materials available for us? So this is again the supply versus demand. So you can see here in 2010, the demand was lesser. The supply of indium was larger. Whereas in 2020, you can see here, the demand is larger and supply is lesser. And this gap would have been increased in the present case, 2023 also, it will be much, much larger there. And you see that where they are used. In the case of flat panel displays, nearly 56% is used in the display devices itself, apart from other applications. So there is a huge demand for this indium tin oxide there. So what we have to do is we have to go for alternatives. So what are the alternatives available there? So there are several alternatives here. In fact, say based upon oxide system itself, you have some alternatives, or I can go for a metallic system, or I can go for a non-oxide and non-metallic systems like carbon-based systems also, I can go there. So if you see here, I have tin oxide doped with some dopants, I can do. Likewise, zinc oxide doped with aluminum, indium, I can do. Or indium oxide itself, I can dope it with some other dopant. Again, indium is a big problem, so I can eliminate this one. Likewise, PaO2 is there. And then P-type copper aluminum oxide is there. Copper chromium oxide is also there. Okay, so all these materials are available for us. Likewise, in the case of metallic system, I can use silver, gold, nickel, copper, and all I can use. Likewise, in the case of carbon, I can use carbon nanotubes. Organic systems also available, PDOT, PSS, graphene, P3HT, PCBM, and reduced graphene oxide. All these systems are going to be available there. But again, remember that all these materials will not have the properties as good as your indium tin oxide. So you have to play with these materials' properties and dopants so that they can be used in a particular sector only. So as I told you earlier, in this particular picture shown over here, I have a spectrum of sheet resistance. So I cannot have one unique alternative material to be used everywhere. So depending upon what is my sheet resistance range, I can choose an appropriate material alternative and then I can use it. That's the point. Okay, right. Now let us see what are the techniques that are available for us to deposit these indium tin oxide kind of alternatives. Okay, so you can see here I can have physical vapor deposition or chemical vapor deposition. So in physical vapor deposition, I can do thermal evaporation or pulse laser deposition, molecular beam epitaxy, sputtering. In chemical vapor, you have both gas phase and solution phase. So wherein I can go for a chemical vapor deposition or an atomic layer epitaxial growth, or I can go for a cheaper technique like spray paralysis, dip coating, spin coating, and all. So let us try to see two different materials, in this lecture. So one, we will coat an oxide system using a spray paralysis, and another one is a metallic system. We'll try to go using a thermal evaporation technique. Right. Let us see what are they. So coming to spray paralysis, which is a chemical technique, is going to be a very cost-effective and reproducible and easy to dope system. Okay. So what we are going to do here is we are going to take the respective metal salts. Say for example, if I want to do a tin oxide, take tin nitrate or tin chloride along with the respective dopant, dissolve in water, and then you compress it and then spray like a perfume. So you know that daily if you use as perfume, you press the head of a perfume bottle, you will see that aerosol is created. The fluid inside your bottle is coming out with a high pressure, mixing with the air, and then comes as a fine particulate. That's what is called as a aerosols. So these aerosols one can create in the laboratory using an appropriate setup, and then I can put these aerosols onto a hot substrate. So once they fall onto a hot substrate, you will see that the solvents will evaporate and the solute will form as a two-dimensional layer after decomposition. So I have to have several control parameters here. Say for example, starting materials, solvent, substrate, substrate temperature, carrier gas, what is the pressure of the carrier gas, flow rate, duration of a single spray. All these things are very important to form a film. And this film formation is given by a Vigue-Spitz mechanism. So wherein you can see that I'll have a substrate, I can put the aerosol droplets onto the surface. So if they're coming to be, they're positioned very nearby, you will see that they will splash from the surface. So if I'm going to keep it very much away, you will see that they may not reach the surface substrate properly. So you have to maintain the distance optimally so that you will see that the aerosol particles will form onto the substrate and they just decompose on the surface of the substrate, giving rise to a proper two-dimensional coating of the oxide layer. Okay, that's called as a Vigue-Spitz mechanism. Right. Let us see more pictures onto this one. So you can see here, this is a perfume bottle. When you press it, it forms an aerosol, fine droplets along with the, a misty kind of droplets along with the solute and the solution and air molecules. So I can take a sprayer and then I can put an aerosol, something like it comes like a cone. So I can have a hot substrate here, heater here, and then I can put the substrate here. So when I spray this one from a particular height, and when there is a temperature given to this, you will see that this fine aerosol along with the solvent and solute, they fall onto this hot substrate, and then the solvents will evaporate out, and the solute will decompose on the surface, and then they form a very thin layer of a film onto the surface. So this is called as a spray paralysis, and the general picture is shown over here. So we can do a simple automation, and then I can do it. Okay. So you can see here, based on this technique, now we have done an alternative material. Say the host material here is tin oxide. So tin oxide, why I have chosen tin oxide in the sense, tin oxide is a very abundant material in Earth. So unlike indium, this is going to be available in huge volumes. So its cost is very, very cheap. Okay. And Yeah, am I audible? Yes, yes. The screen is visible to you all? Fine, okay. So sorry for the interruption, there was a power cut. Right. So now, as an alternative material, what we can do is, we can try to dope tantalum into tin oxide. So tin oxide, as I told you, it's being a very cheap material and abundant. You can try to dope tantalum. So tantalum, when it goes into the tin side, it is going to exist in a +5 charge state. So for SnO2, you will see that oxygen will be 2-. So there are 2 units. So oxygen will be in 4- charge state. So tin will be in +4 charge state. So instead of this +4 charge state, if I'm going to put tantalum here, so tantalum will exist in +5, which means that it is going to give 1 electron, free electron to the system. So that way it is going to be act as a donor system. So when I try to put different concentration of tantalum into the system, this is going to serve as an effective alternative transparent conducting oxide. So remember that in ITO, what we had was 90% of indium, In2O3, and then 10% of tin oxide only we had. Okay, so in case you see that the usage of indium is very large here, whereas in this tin oxide, you will see that I can go only up to a maximum of just 5%. So I will have 95% of tin oxide and then just 5% of tantalum doping. So tantalum is also, is going to be an abundant material comparatively, and the usage of tantalum is only mere 5%. So this way, this is going to be a very, interesting system to act as an alternative transparent electrode. Right. So this is the spray pyrolysis unit which we designed it, and these are all the parameters and precursors which we are going to use. Say tin nitrate, tantalum chloride, or tin chloride, tantalum chloride we can take. So it can be shifted. You can use even tin nitrate, tantalum nitrate, or tin acetate. All these things, there is a flexibility there actually. So that is the advantage of this technique. You can have several kinds of precursor and several types of solvents you can avail here. And substrate temperature will be 400 degrees centigrade. I can simply use air only there. And then I can spray the solution onto the surface of the substrate, and then I can try to form the film. So when I do the film, you can see that this is pure tin oxide, 1, 2, 3, 4, 5% of tantalum. So I'm going to vary the doping concentration, and then I can confirm the phase that is going to be formed. And you can see that this will have a texture growth. So it is going to be more oriented along a particular plane direction only. It is going to be there. So that was estimated from texture coefficient using X-ray diffraction. And then coming to the charge state. So I can do an X-ray photoelectron spectroscopy, and then we confirmed that the tantalum is going to be existing in +5 charge state. So which ensures that this is going to act as a donor into the SnO2 system. And then coming to the morphology, there is nothing new here. It almost has tetragonal shaped particles of tin oxide, and the composition is also confirmed from EDEX also. And then coming to the optical properties, this is going to be interesting. So you can see here our tin oxide is going to have somewhere a transparency here. So upon doping with tantalum, you can see that 4% tantalum doped sample is going to have higher transparency, more than 80%. So in fact, this is a good sign that the transparency is going to be really good. And I can even calculate the band gap of this system by making a tau plot. And then the band gap is around 3.9 electron volt. So if you see the prerequisite for an TCO layer, the band gap should be larger, and transparency also should be more than 80 or 85%. So this is almost a very good alternative material with a high transparency and then also a wide band gap. Right. Now coming to the electrical properties. So what will happen to the sheet resistance with respect to tantalum doping? So if you see this x-axis here, this is pure tin oxide, 1%, 2, 3, 4, 5% tantalum doped system. So as you see here, the sheet resistance for pure tin oxide without any dopants was more than 1000 ohm per square. So when I start doping with tantalum, you see that it comes down and it is a minimum for 4% tantalum doped system. So it's almost like 15 to 20 ohm per square was achieved here. So this is almost like our commercially available indium tin oxide. Okay, and even you can do an Hall effect, and then you can calculate what is the mobility and concentration. If you do that, I can see that I'm going to have a higher mobility for my 4% doped sample. Because, for its applicability in a device system, the charge carriers have to move faster. So then only, the conductivity will be very effective. So the mobility also should be larger here in this case. So likewise, I can also do a temperature dependent property to study the thermal stability of this sample. Because, to fabricate devices, we are going to have different processes involved. So wherein you should have always, a higher temperature for device fabrication. So I can even do a thermal stability. So this table shows you a collective optoelectronic properties of the deposited tantalum doped tin oxide. Okay, so you see here the band gap is larger. In fact, for 4%, it was 4.01 electron volt, and then you can see the carrier concentration is of the order of 10 power 20. Likewise, mobility is larger, 45 centimeter square per volt second, and then the sheet resistance you see here 17.9, almost 18 ohm per square. So commercially available tin oxide ITOs will be around 10 to 12 ohm per square. This is just 4 or 5 ohms excess, so which means that it's nearly on par with ITO. Band gap is also larger. Sheet resistance is also lower here. So this shows that for concentration variation, 4% tantalum doping into tin oxide is an effective TCO system. Now let us try to map the sheet resistance, because we are doing it by a spray per resist technique. There will be some deviations. So this is not as good as your physical vapor deposition. So there will be a deviation. So what we did was we made a 10 centimeter by 10 centimeter square area, larger sample, and every 1 centimeter by 1 centimeter was measured for its sheet resistance. And then we have made a contour plot like this. So as you see here, the center part is very low in sheet resistance, nearly 19 ohm per square. Whereas the peripheries are going to be larger in sheet resistance, nearly 68 ohm per square. So this comes from the slight irregularities in the deposition process. But one can modify this by putting multiple spray gun and other parameters. You can make this much more uniform, in sheet resistance. Right. Now coming to the temperature stability. So what we have done here is we have annealed this sample for different duration at different temperatures. Okay. So if you see indium tin oxide can withstand only up to 300 degrees centigrade. So beyond 300 degrees centigrade, the sheet resistance of indium tin oxide will be increasing enormously. Okay. Whereas in the case of tantalum doping system, you can see here, for heat treatment at 400 degrees centigrade. Okay. So which is a kind of orange color, you can see here. So the sheet resistance is actually decreasing here. And as a function of duration, if you see here, up to 2 hours, it is okay. The variation is only up to 70 ohm per square. So if you maintain it for only 30 minutes, most of the process, it will be only for a short duration. So if you do it only for 30 minutes, you can see here, the sheet resistance is lower, okay, for 400 degrees centigrade. And then for 30 minutes of treatment, it increases only around 30 ohm per square. So it was nearly 18 ohm per square. So it's nearly double the value, that's all. But if you increase the duration, then it increases drastically. And again, more than 400 degrees centigrade, you see here the sheet resistance increase is much larger in this particular case. So which means that you can comfortably use it for 30 minutes up to 400 degrees centigrade, which is much better than commercially available indium tin oxide. So the thermal stability of this sample is also really good. Right. Now we can also calculate the surface work function. What is the energy required to pull out an electron from the surface? You can see here it's going to be really good. So for tantalum doped system, I'm going to have 5.7 electron volt as the surface work function, which helps this sample to make a good quality device, because the surface work function is also reasonably good compared to indium tin oxide available. And coming to the application part, so what I can do is I can make a device system using this tantalum doped tin oxide. I can make a dye sensitized solar cell. Okay, I'm using this as an electrode. So instead of ITO or instead of fluorine doped tin oxide, I can put this tantalum doped tin oxide, and then I can make a device in this structure. So these are the coating processes to make a device structure. So once we have made this device structure, you can see here. So we have made 2 devices, one with 4% tantalum and another one with commercially available fluorine doped tin oxide, which is also an alternative system. But it is thicker in film, and its transparency is lesser. But tantalum doped tin oxide transparency is much larger compared to your FTU. Right. So if you see here, I can see a very nice IV curve, and the efficiency wise, for commercially available system, it was around 5.5%. For us, we got it 3.2. Again, this commercially available one is made in the industry, so they will strictly follow all the conditions. But this is a lab scale. So for a lab scale system, the efficiency is more than 50% of the commercially available system. So it means that you can tune these properties to make this as an effective alternative system that is already available in the market also. So the performance is also really good, transparency is good, sheet resistance is also very low, and carrier concentration mobility is also really good here. Right. So this is about the oxide system. Now let us try to go for a non-oxide system. Okay. So in a non-oxide system, we can use noble metal systems to make these alternative systems. Again, for the same reasons that indium is very scarce in Earth's crust, so we are going for an alternative system. But the problem here is these are metallic systems. So you know that metals are not transparent to the incoming radiation. Already we discussed, but they are highly conducting. Okay. But now, if you see carefully, metals are in fact partially transparent to the incoming radiation, mostly visible radiation, provided if you reduce the film thickness beyond a certain limit. Okay, so if you see your Maxwell's equation in EM theory, you will see something called as a skin depth. So the skin depth is a thickness up to which the electromagnetic radiation can penetrate through that. So if my thickness is larger, the penetration only will be up to a particular distance, and after that it gets absorbed by the free electrons. So what we can do is we can coat our film into a very thin layer below the skin depth of the metal. Then it should be partially transparent. So this is the logic here. So we play with this skin depth, and people have already reported for silver, gold, and copper and nickel, I can coat a very thin layer of my material, and then I can try to play with the transparency and conductivity. Okay, so this is the logic we have taken. And you see here for silver, gold, and copper, they are transparent only for a particular wavelength only. For all other wavelengths, the transparency is lesser. So what we thought here was, why don't we combine several materials into a stacked layer so that we can enhance the transparency for all those particular wavelengths also. So that was the logic here. So for that one, we adapted a thermal evaporation technique. Okay, so wherein you will have a thermal system where I can have a board, I can apply a huge current, and then I can increase the current to, say, for example, 150 ampere. It will do a resistive heating, and then I can evaporate the sample which I am keeping it in that board like this. It can evaporate. So I can keep my substrate here. I can coat it on the surface of my substrate, the metallic system which I am going to take inside my boards here. Okay, this is based upon Joule's heating effect, I square RT, system. So when I apply the current, depending upon the time and my resistance of my board, I can evaporate a system. So what we have done is, in this thermal evaporation technique, we have taken gold, silver, and gold, and also we have taken copper, gold, and copper, silver, and gold in this structure. So you see here in this system, we are maintaining gold only 2 nanometer, just 2 nanometer, and silver 4 nanometer, again top as a 2 nanometer. So why we are going to use this top gold layer in the sense, the silver is prone to oxidation. Okay, so if I don't coat top layer, you will see that this will be oxidized very quickly. So to prevent this oxidation, I'm going to give a capping layer of 2 nanometer thickness of gold. And bottom gold acts as a seed layer. So this is going to give a good growing properties for the silver. So total, if you see that, it is only 8 into 10 power minus 9 meter. So it's very, very thin, just, a 8 nanometer coating only we are going to give here. Okay. But here you see that this is going to be coated on a polyethylene terephthalate substrate. So it's something like your OHP sheet. So this is highly a flexible one. Okay. Right. So on a flexible sheet, I can use thermal evaporation, and then I will coat first gold, silver, again gold, because I will be having a 2 electrode system in this thermal evaporation. So without breaking vacuum, I can coat 2 different materials there. It is possible here, right? So now we have made 2 systems here actually. One with copper, silver, and gold. Another one with gold, silver, and gold. So you can see here, I am comparing this one with commercially available indium tin oxide. So indium tin oxide is also commercially available on a flexible substrate. Okay. So as shown in this particular picture here, this is commercially available one, and this is gold, silver, gold, and this is copper, silver, gold. Now you can see that visibly there is a variation in the transmittance. And also in the UV visible spectrometer, you can see that commercially available ITO, which is shown by blue color, has a peaking around 570 nanometer. Okay, whereas when I use my copper component, the transmittance is coming down. Whereas when I use my gold, silver, gold, you see that the transmittance is also larger, red in color, and is also very stable for a wider range of wavelength. This is the point here. So that's why we did not make an individual layer. We made a combination of these three materials, and then we have extended the transparency to a larger region of the wavelength. Okay, and of course we did X-ray, but it's a very thin layer. We cannot observe any crystallinity there. Right. Now we have to go for the surface analysis. Now in the surface analysis, you see that it is going to have island-like structure. So I'm seeing some material here, and some gaps are available here. Okay, so this may be forming an island growth. So now you recall the growth methodology which I told you, Walmer-Weber growth mode or island growth mode which I told you earlier. Okay, so this is the island growth mode. That's why the film is not continuous. Okay, for a particular layer. But the bottom layer is exposed here. But again, see here, these are metallic systems. So when they come into contact with each other, there is a continuity for the flow of current. So this is the advantage. So though it's an island growth mode, you will see that there is a continuous path between the particles. So it's going to be highly conducting. So if you see the sheet resistance, you can see here for commercially available indium tin oxide, it was around 5 ohm per square. For us, for the copper system, it was 7.7. For gold system, it was 10 ohm. So it's not very high actually. Just double the sheet resistance of commercially available system. Right. Now we can also calculate the figure of merit. So based upon the transparency and sheet resistance, we can do a figure of merit using this formula. And you can see here the figure of merit is also really good as compared to that of your indium tin oxide. Right. Now we can also do the Hall effect and to calculate the transport parameters. What is the carrier concentration? What is the mobility and all? So if you see that for indium tin oxide is 10 power 22 because it is an oxide system. So obviously it will be higher. But if it is a metallic system, it is much more higher because we have only free electrons. So the carrier concentration is really good. Okay. But coming to mobility is actually slightly decreasing compared to indium tin oxide because there are more number of electrons. They have inter-carrier scattering. So the mobility part comes down. Okay, that's the point with Hall effect, but still the mobility is reasonably good. Now, because it is done on a flexible system, I have to test how flexible is my material. Okay, so I can go for designing a bending twisting equipment. We designed in our own lab and set up to bend it and twist it because these are very thin films on a flexible substrate. So we have designed this one based upon commercially available Arduino system, and our students did a programming for this, and then we have integrated it. And finally, we could make a device system like this. So we can do a bending and also twisting is possible. But this video shows only, a bending. So you can simply use a C programming system, language, and then you can do this Arduino, and then you can control this one. So the one which is bending here is actually our coated sample. And we can even put an LCD system there, and then I can even calculate or count how many number of bendings and twistings are happening there. Okay, to test the stability of my coating. That's the point here, right? Now coming to the flexibility analysis, I can do both inward and outward bending, and then I can measure the electrical properties. So when you are done the machine, we have just tested first with ITO on PET, okay, commercially available system, to see whether this machine is working properly or not. So when we are seeing that one, so after 1000 bendings, you see that the sheet resistance increases drastically up to 5000 bending, which means that the machine is actually imparting the stress and strain to the system. And ITO, because it's an oxide system, it cracks very easily. So it cannot withstand beyond 5000 bending and twisting. You can see visibly some kind of striations are found on the surface. Now we are testing this one with our tri-layer, metallic tri-layer. So when you go for the metallic tri-layer, in comparison with our indium tin oxide commercially available PET system, you can see beyond 5000 bending, there is a drastic increase in the sheet resistance because the material is damaged there. But for the metallic system, you see here, up to 50,000 bendings, it's nearly the same. Just 1 or 2 ohm resistance increase only is there. So because it's a metallic system, it can be easily bendable compared to your oxide system. Okay, so the stability of your bending and twisting on the sheet resistance is really good. Up to 50,000 bendings also it can withstand, or even more than that, it can do that. Right. Now coming to the Scotch tape test. As I told you earlier, we put a tape and then we have peeled it off several times. and tested for the resistance, it was no greater change was observed. It was nearly the same even after tape test, and it was highly conducting. You can see here I am putting a wire with a battery backup, and then I can glow an LED here. So it means that, though it is thin and transparent, it can easily conduct the current, and then it can glow an LED. These are the tests which we have done on the sample. Now we can even go for a device fabrication. So we have done a polymer solar cell using this system, which is actually bendable. So you can see that the dots here are actually a device structure of this structure, and then you can do that. But the performance was a little bit poor because one has to optimize it. So the performance was not really good there. Okay. So anyhow, I will stop for sputtering. I will only limit to the thermal evaporation, and then we can make. In fact, you can make using a sputtering also. As I told you, using sputtering also we have used for platinum. So I can put a gold, platinum, and gold. All these three noble metal. Again, you see here, this is only 6 nanometer, and this is highly crystalline because I do it by a sputtering technique. This will form nearly a layer by layer growth mode, as observed by this particular interference pattern coming from the X-ray reflectivity. So these are very good quality sample. And then using this sample, I can do some contact angle measurements. Again, I can measure the transmittance. You can see that how nicely it is bent. And then I can make an electroluminescent device using the sputtered thin films. So you can see here, when I make a device structure like this and I apply a current, it can glow like an orange color. Likewise, it is transparent both top and bottom layers. When I put a UV light for a particular phosphorus material there, it can glow. So you can see this one. This is when I put a UV light, it is glowing, which means that the light emitted is actually coming outside the electrode. So which is a proof that the top and bottom electrodes are actually transparent there. Not only this, you can even make a surface analysis and other kind of optoelectronic properties, and then we can make a piezoelectric generator. Okay, so I can put a zinc oxide, and then I can put my top layer as a contact layer, bottom I can make an aluminum foil. I can grow this zinc oxide, and then I can try to tap the surface. So when I tap the surface, zinc oxide being piezoelectric in nature, it is trying to generate a small amount of output voltage, so which I can convert it for my power harvesting. So I can coat it, and then I can use it as an effective electrode system for a piezoelectric nano generator also it can use. So these kind of alternative materials are going to be highly applicable for several of the optoelectronic devices. So in fact, you can do a lot of fine tuning, and then I can achieve all these properties here. Okay. So I will stop here, and I thank my collaborators and also for you for listening patiently. Thank you very much. Madam, am I audible? Yeah. Any questions or clarifications?
Participants,
Yes, madam. Noise is there, madam? Yes, madam, you can do. First, you have to make an ingot alloy, and then you can evaporate it to form a thin film. It is possible. But, the temperature is limited only up to 1000 or 1100 degrees centigrade. You cannot evaporate beyond that. Very high melting point systems, you cannot try to coat it here. Because gold and copper are low melting point systems, you can easily coat it. We can do sputtering, madam. As I shown in the last few slides, we can do a sputtering technique, but you need an expensive target and an expensive system there, which is much higher than your thermal evaporation technique. Thank you.
Sir, I have one question now.
Yes.
What are the orders of the vacuum required to grow these films?
For metallic systems, we need 10 power minus 5 torr in a thermal evaporation unit. Okay. In a sputtering unit, if it is a very good system, it can even go up to 10 power minus 8 torr. But for the oxide system in spray pyrolysis, we have done it in ambient. Only there is an increase in the substrate temperature. In a normal air atmosphere, you can do. You don't need any vacuum because it's already an oxide system. Even if it oxides, nothing to worry.
So suppose if we have our own vacuum chamber system constructed by us with a rotary pump, is it possible to grow these films, or it is difficult?
Metallic systems, it is difficult, because copper and all is highly oxidant. It can oxidize very easily. Yes, so you should definitely have a diffusion pump.
Yes.
Supported by your rotary pump. Then only your vacuum level will go up to 10 power minus 5 torr.
Minus 5.
If you try to do it at 10 power minus 3 torr, if you use copper or silver, they get oxidized. You can do gold. Gold is possible. But again, gold is very expensive there. So you cannot go for a very, large amount of volume. That's the point.
Yes. Thank you, sir. Thank you very much.
Thank you.
Sir, another one question, sir.
Yes.
What were the magnetic fields you used to study the Hall effects?
Hall effect, it was around 0.57 Tesla.
Pardon, sir?
Around 0.57 Tesla.
0.75 Tesla.
0.57. It's a standard one in machine like Ecopia HMS. It's a Korean company. So in that machine, it's a standard field, 0.57 Tesla.
Usually in these metallic films, to get the Hall coefficient or the Hall voltage, to generate the Hall voltage, such as thin films, these are of the orders of nanometers.
Yes.
Detecting that Hall voltage itself is a big task. Am I right, sir?
That is true. That's why, we use gold tips in that machine. And you have to do a couple of trials. It's not quite easy, as you say, because the films is very thin. But again, it's highly conducting.
And the development after this Hall voltage will be very difficult especially in the metals.
Yes, that's true. That's true. That's why you use a sensitive machine to do that one.
Which one you have used to say?
Hall HMS 3000, Ecopia HMS 3000 is the machine which we have done.
Okay. Another one question is there.
Yes.
This Hall mobility, what you have observed, will it be the same as when I excite these materials with the certain radiation and I will record the lifetime of that one? So using that lifetime, I will calculate the mobility with the mass and the charge of the electron. Both are going to be the same or they are going to be the different ones?
I don't think they will be same. See, again, it depends upon what is the radiation you are going to put there. We have not done such kind of measurements. We have not done, in fact.
Suppose the energies of the radiations, if they are equal to the energies of the magnetic field, then would it be the same or they are going to be different?
I am not very sure about this because, the radiation which you are going to put has to really influence the free carriers.
Yes, sir.
Because this mobility is dependent upon carrier concentration also.
Yes, sir.
Not only that, the defect density in your system will also affect it. Say if you are going to have island growth mode, a lot of scattering will be there.
Yes,
or if it is a very nice layer by layer growth mode, the mobility will be really good. So it all depends actually.
And what were the contributions from the interface roughness fluctuations actually in these films? Because the
interface roughness will be there.
Correct. Fluctuations.
Yes.
They will hinder this transport very strongly, I feel, sir.
It will. See, for example, there is an interface here. If you recall this UV visible picture which I have shown over here.
Yes, sir.
You can see that at this point, you are having a lot of interference there.
Yes, sir.
In the UV visible pattern. In fact, if you zoom it, here also you will have it. Okay, which means that they have a layered structure. But again, that is why the mobility is lesser here. You see here, the mobility value is only, very low here in this case. Yeah, mobility here is only 10 centimeter square volt second for commercial.
Very low, very low, very low.
Yes, in our case also you see here very low, but you see the carrier concentration 10 power 23. That is
Very
another
high.
reason, because they have a lot of intercarrier collisions there.
Yeah,
So
very high
obviously
carrier
mobility will come
concentration.
down. This is the point here.
Yes, sir. Yes, sir. Yes, sir.
But what we need in industry is for display applications or solar cell applications, people expect that around 70. Currently, they want more than 70 or more than 70. It's beneficial.
Another last question, sir. Can you suggest simple experiments that can be done in the laboratory to analyze these things, not at the industrial level, prototype?
I mean, you are talking about Hall effect?
Not the Hall effect, just these TiO2 films which you shown for the photovoltaics applications or for the.
You can very well go for this spray paralysis techniques, because
yes,
this spray paralysis, in fact, one can do even with this kind of a perfume atomizer.
Okay.
With a hot plate, you can do. But only point is how nicely you are filling it and what are the parameters you are able to repeat properly. Even you don't need this kind of setup here. People have published paper even with this atomizer itself. With a normal hot plate, you can put a substrate. You can take some chlorides or nitrates of your say titanium or zinc or even tin. You can spray it from a particular height. Fix the temperature something like 250 or 300 on a hot plate.
Yes,
you will get a film here very easily.
Thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you, madam. Thank you for the opportunity. Thank you and all the best. Thank you.
Am I audible, ma'am? Yeah, thank you so much for the nice introduction, ma'am, and the opportunity from the physics department of Equinox College. So, may I know the time limit, like till when I can hold the session? 40 minutes from now? Okay, yeah. Thank you so much, ma'am. Thank you. Just give me a second, ma'am. I'll just share my screen. Yes, ma'am. I'm trying to do it. Just hold on for a second. Hello, ma'am. I'm not able to share my screen. Is the option disabled? No, I'm not able to click the share option now, so I'm just looking on for it. Just Ma'am, just give me a minute. There is an issue with the screen sharing. I'll just change the privacy setting and get back to you. Just 2 minutes. Yeah, sorry. Okay. Hello, ma'am. Can you hear me? The thing is, like, I have to change the privacy setting in my Mac. So just a second. Okay, then that will be great. I'll send you a mail, ma'am. Yeah. Yeah, sure. Yeah, sure, ma'am. Sure. Is it the same mail I've received, or should I use a different email, ma'am? I think it will come in Drive. Same mail ID. Okay. I think it will come in Drive a bit bigger size. Yeah. And I'll email my presentation. Okay. So, okay. Yeah. Yeah. That's fine. So shall I start, ma'am? Yeah. 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 Okay. And shall I start? Maybe the introduction I'll start. Okay. I'll just start the requisite thing, and when the results come, I'll start. Yeah, fine. Please let me know once it's open, okay? Yeah. Hi, good afternoon to all. So today I'll be looking on explaining things on, I just want to have an overview of the evolution in the electrochemical energy devices. So I am actually working in Nanometals and System Laboratory in Faculty of Applied Energy Systems, Department of Mechatronics, Jeju National University, South Korea. So why do we need an electrochemical energy storage system? So as we all know, we are marking towards the carbon neutrality, the mission towards carbon neutrality in 2050. We should have been achieved by 2030. Though can you hear me, ma'am? Okay, yeah. So why do we need an electrochemical energy storage devices? So as we need to march towards the carbon neutrality in order to protect our environment and make it a green for our next. Yeah, thank you. So the first one is like, I want to explain the evolution and the overview of the electrochemical energy devices in the current scenario. So as you all know, the second slide, ma'am, the global demand and the carbon neutrality, the CO2 emission annually, it's been increasing over the globe. So as you can see, India is nearing like 5 million ton of carbon neutrality, like carbon dioxide emission. Since our nation has made it the point to march towards 2050, we are more focusing on the renewable energy generation. Once the generation of energy is done, you need some devices to store those energies. So that's where the electrochemical energy storage devices comes into a main picture in this current scenario. So of the electrochemical energy storages, we have supercapacitors, also battery. Those two things are the electrochemical energy storage devices. In terms of battery, if you see, they have a higher energy density, but supercapacitor has a lesser energy density. The power density of both the devices, if you see, the power density of supercapacitors is more. The cost-wise, the charging speed, and the lifespan, and the materials used, you can use in supercapacitors the eco-friendly materials or towards the green materials. So battery also they are marching towards. So the major focus of this talk will be on supercapacitor-based electrochemical energy system. So as I told, I want to focus more on the evolution of electrochemical energy storage devices. So as you all know, there are the supercapacitor has the configuration as like positive electrode and the negative electrode with the electrolyte. In terms of liquid, if you use a separator in between. So that constitutes a supercapacitor. So if you go for a gel type devices, then you go for a solid state devices. So if you see, the electrodes and electrolytes should have the synergetic effect in order to give higher performance. So depending on the need of like where you want to imply the supercapacitor, the choice of material should be in that way. So if you see that once the supercapacitor is generated, that's what the storage devices is done. The harvester part. So as I told, I'm going to focus more on the evolution part of the electrochemical energy storage devices. In the next stage of supercapacitors, they are called as integrated energy systems or self-charging power cells or self-charging supercapacitors, where you don't need any other external electrical as the input to harvest and store. So the major, we are just focusing on waste biomechanical energy utilization. Like the first one in the slide 3, if you see, the force or the piezoelectric nanogenerators, and the next one is the triboelectric nanogenerators, and then these are like thermoelectric nanogenerators, and these are photovoltaic cells. So these are generators, And in terms of storage, as I explained previously, the supercapacitors and battery. Once we integrate these two systems of harvester and storage together, there are some internal circuits should be used in order to convert the generated current or the power to store it to the storage devices. Then only we can be using it for a longer duration. So there, the power model circuit is very much needed for converting it from the harvester to the storage devices. So once if you see, as you can see the right corner in the third slide, you can see the casting current collector, the electrodes, the separator, the electrodes, and again the current casting collector. So this is the configuration if you're using a supercapacitor in a solid state. So if you're going to harvest with the same device and store in the same device, the mechanism of it is going to be different. So, but if you use a harvester separately and a storage device separately, you need a module like the power circuit module, which can connect your harvest and storage devices. So in the supercapacitor configuration, as I told before, if your electrolyte, what are the, actually the current focus is majorly on the electrodes part, but there should always be a synergetic effect of the importance should also be given to the electrolytes as well. So what are the conditions that the electrolyte should hold are there mentioned in this fourth slide, right side bottom, the pie circle. So if you want to increase your power density, then you should concentrate on the potential window, the ionic conductivity, and the ion electrode material interface of the electrolyte. In terms of capacitance, if you want to focus, the electrolyte you should match the ion size of the electrolyte to that of the electrode surface, matching the pore size of your electrode material and the ion size of the electrolyte. And if you want a lesser ESR, this is the solution resistance. You should have higher ionic conductivity and higher mobility, and it also should be viscous. If you want to focus on the thermal stability, you should be taken care of the nature of the electrolyte, how it's like, what is its salt solubility, boiling point, and freezing point. If you're focusing to develop the energy density of your device, of your storage device, then you should focus on the concentration of the electrolyte and those stuffs, which matches to that of the electrode's pore size. So these are the conditions which you have to be focused for electrolyte in terms of electrochemical energy storage devices. So on an overview, the electrode should have a dimension reduction, so which enhance the faster ion and electron transport, and high surface reactivity is very much needed. So the reaction takes place at the surface level and it does not penetrate through like a battery material. So a supercapacitor and a battery, if you want to differentiate in a very simple way, so you can just like think of a tap. So if a bucket with a tap at the bottom. So at the bottom, if you just open the tap, it's like how fast you open, your electrons or like the water will flow out. It's the same way your supercapacitor, once it's charged, it will discharge at a faster rate. So, but if you're using a battery, it's like a dam. So you'll store and then it goes in a very slower time. So that's what it meant in higher power density in supercapacitor and lower power density in battery. So in terms of charge storage mechanism, in terms of supercapacitor, as I told before, I'll be majorly focusing on supercapacitors. There are like 3 types of storage mechanism where the supercapacitor is being like studied. So if it is a surface reaction, it's happening, it's called as type A capacitive. So the electrolyte ions do not penetrate, or the surface reactions only happens at the very, very surface, or it's called as the electrostatic storage method, like where your Helmholtz double layer is formed when there is an interaction with the electrolyte ion to that of the electrode at the surface level. So if you can see the slide 5, type A on top, A, B, and C, there you can see it's only the surface reaction. So the first one is like very sharp, only the electrostat, little surface reduction, like redox peaks, you can see just a wavy thing. So the ideal thing you can observe only in carbon-based material. If you go on for other based materials, then it won't be an EDLC behavior. Or if you have a very pure carbon material, there will be only electrostatic force. But if you have a free groups that can react with the electrolyte, then it undergoes surface redox. So if there is other 2 types of charge storage mechanism, where type B is pseudocapacitive, where there is an intercalation. So intercalation, what I meant is like at the surface of electrode, when the electrolyte is penetrating, it penetrates to some extent and then comes back to that in the discharge state. So the time allowed for the electrolyte ion to interact with the electrode will be comparatively less. So that's what it states. And in the next we can see the intercalation. So the CV, as you all know, for a supercapacitor, the more basic thing to do is like measure a cyclic voltammogram. In a cyclic voltammogram, if you see the behavior, the intercalation means like it goes a sharp inside, as you can see in the D figure. So if you see the E figure, it's also you have a partial redox peak as well as it's diving inside the electrode surface, but still it's not going through very in. So that's the partial intercalation with partial redox storage mechanism, so which comes under type B pseudocapacitor. So if you're going for the other storage part, which is Faradaic, which is mostly in the battery-based materials, you observe CV, like cyclic voltammograms, like Faradaic dominated, and typical batteries, you observe these kind of studies, like these kind of observation you'll be studying in your material when you're doing the like in sulfides or like selenides or even some battery materials, you'll observe this kind of peaks. So the integrated the next slide, ma'am. The integrated energy system. So I have been mentioning on mechanically or piezoelectrically driven self-charging power cell. So the power cell has, as I told, there is no need of any external electric current to pass through. Your waste biomechanical energy is being utilized for the harvesting, like for harvesting the energy, and that is being stored with a supercapacitor. That is the overall view of this this presentation actually. So that's what I meant, the next generation electrochemical energy devices or the evolution of energy storage devices. So the merits and the issues of like when the movement is in your neck or like in the when moving your wrist, or there is a movement even when you're placing it under your foot or like under your shoes, there will be piezoelectric generator be placed separately, and you use a circuit module to convert it from AC to DC and then store it in your storage device. But if you're going for a self-charging supercapacitor power cell, it's all being integrated in a single device, and you harvest and store in a single device without any power conversion module or the power management circuit being used. So if you see the merits, they are low manufacturing costs, they are maintenance free, and they are mostly in wearable applications. But the issue is like still, since all these are in the lab scale, there will be poor energy conversion efficiency, and the understanding is like it has been less than a decade, the evolution of this self-charging supercapacitor power cell. But still, the understanding mechanism is like, because if one issue is solved, we are obtaining with other issues where we can't increase the conversion efficiency to a greater level. So the overview of the system, what I'm going to present today would be on the integrated system. The first part I'll be focusing on the next slide, ma'am. The first part will be on proton conducting electrolytes be used with the in order to study the electrode property. We first initially do the 3 electrode analysis, and if the 3 electrode analysis is giving a better output, so then we can go for the device. So the first part is like a 3 electrode analysis with the proton conducting electrolytes in aqueous. And the next system I'll be explaining with antimony sulfur-iodide with TaBF4 as ionic liquid electrolyte in a coin cell configuration. And the next thing will be like tellurine-based carbon cloth ionogel devices, where the wearable and it's an extrinsic device. And the next I'll be focusing on naphion-based triboelectric nanogenerators, and then a supercapacitor is being integrated with an external, like it's called as with a power management circuit, and it could be used also in wearable applications. And the next one will be for the higher power for the next generation hybrid electric vehicles. If we place the supercapacitor in the regenerative braking system, the supercapacitor captures an energy and also it saves the battery's life. So we have tested that prototype as well. And finally, as I told, in a single system, a single device which can harvest and store without any power management circuit. So that is called as a self-charging supercapacitor power cell, which is completely intrinsic. So this is the overview of the system, what I'm going to present today. So the first part will be, I've used electrode. So as I told before, we should have a very keen understanding of the electrode as well as on the electrolyte, in order to obtain the very better or like the needy requirement, or like where you want to go and where you want to place it for your application. So if you're using an activated carbon-based electrode material, this has been done with a normal slurry coating, with a handmade slurry coating. To study the 3-electrode system, or to study the electrode, we approach towards a 3-electrode system. And the electrolyte what we have tested is like proton conducting electrolytes of ammonium thiocyanate and ammonium nitrate. And we have tested the physicochemical analysis of activated carbon, the X-ray diffraction analysis, and the coated sample. The FESM images shows the coated sample distribution in the electrode surface. So the current collector what we used is stainless steel to study the exact behavior, because we can't coat activated carbon or carbon cloth. So we doesn't know like what is the actual contribution from our electrode material. So we have used it with a stainless steel electrode, and the DET analysis to analyze the pore size and the observed relative pressure analysis, which follows the ICCMPM model. And this is the electrochemical characterization of the activated carbon. Here, if you see the cyclic voltammetry, here, if you see in slide 10, figure A, the cyclic voltammograms of activated carbon with ammonium thiocyanate, and B shows the cyclic voltammogram of the ammonium nitrate. And here you can see the specific rate and the specific capacitance, which is scan rate dependence on the CV, and below depicts the CD of the same ammonium thiocyanate and ammonium nitrate. Though in this interpretation, though ammonium thiocyanate has given a very higher result than the ammonium nitrate, the stability was more in ammonium nitrate than cyanide, because the cyanide group, like, it started affecting the electrode material over a longer duration. So we plan for testing the ammonium-based proton-conducting electrolytes, since we are focusing more on proton-based proton-conducting electrolytes. If you see the mechanism of ammonium-based proton-conducting electrolytes, as I told before, the mechanism of charge storage mechanism, the surface reaction happens only in carbon-based materials. In oxides and sulfides and selenides or iodides, if you go, there will be partial type B storage mechanism. It's not only electrostatic, there'll be free end being reacted with your electrode surface. So whether your electrode is only reacting or it's degrading, it depends on the choice of the electrolyte what you're using. So at the surface of the activated carbon, when it's coated on the stainless steel substrate, the proton adsorption for the charge storage at the electrode you can see, and the intercalation of the storage what we have mentioned is like it. If the carbon-based material or activated carbon is very pure and you don't have any free functional groups attached to it, there won't be any reaction with the electrolyte ions. If you have a free ion, it will obviously interact, or it is just at the surface the reaction happens. So the electrochemical impedance analysis of like pre and post. Here we have studied the post analysis after once the electrochemical analysis of cyclic voltammetry, the galvanostatic charge discharge analysis. Impedance is done. Body phase angle is being analyzed. Then we separate the cell and we test how the morphology is being changed or not through FESM is being analyzed. And through Raman analysis, we have analyzed what is the ID by IG ratio and how it is being different after the analysis of the proton conducting electrolytes with the electrochemical reactions. So this was the first report with ammonium based proton conducting electrolytes. So in overview, we have discussed the charge storage mechanism of activated carbon electrode using ammonium thiocyanate and ammonium nitrate electrolyte. So the electrochemical impedance analysis showed ammonium-based proton-conducting electrolyte showed minimal resistance, which means the reaction time of the supercapacitor or the turnover frequency is very less for when you're using ammonium-based proton-conducting electrolytes with the activated carbon for supercapacitors. So the next system I'll be focusing on will be antimony sulfur iodide the first one was with a liquid or aqueous based system, and now we are going towards ionic liquid based system. So in 3 electrode, as I told before, initially we have to test with the 3 electrode system to understand the electrode. So that we call it as like half cell or 3 electrode analysis. So antimony sulfoiodide is being the electrode, and ionic electrolyte is TaBF4. So if you see, this is a coin cell type configuration. So the previous one is like in a liquid, which is open in a liquid cell. So this one is a liquid system with a coin cell configuration. So the antimony sulfoiodide is prepared through ultrasound irradiation process, and nanorods are being generated, and we have fabricated the device with a CR202 coin cell, and we have analyzed it with a for the higher electrode capacitance of 161.61 farad per gram, like which is compared, like other than carbon based materials, this we have got a higher results in terms of capacitance. So if you see the morphological analysis of FESM analysis, we can see the rod shape, which is like with a dots grown on it, and the distribution of antimony, sulfur, and iodine is being shown in this slide. So if you see the physicochemical characterization of antimony sulfoiodide, we have shown the physicochemical analysis and also the XPS peaks of like it's a survey spectrum, and the remaining or the SB peaks and S peaks and the iodide peaks. So the electrochemical analysis we have done, once we start the experiment, the eagerness of the choice of electrolytes will like made me to work on 2 or 3 multiple electrolytes. So whichever the electrolytes is better or which is most suited for the electrode, then we can proceed towards for the higher output or higher efficiency. So I have also tested with the liquid electrolyte of sodium hydroxide. When sodium hydroxide is tested with the antimony sulfoiodide, we have obtained the cyclic voltammetry and the galvanostatic charge discharge and the impedance, and we've also done the cycles of like 3000 cycles. So the electrochemical analysis of antimony sulfoiodide with TeBF4 electrolyte is being tested. So where you can see little bit intercalation with the redox peaks being observed in your CV, and the galvanostatic charge discharge analysis, and the device capacitance, which is the current rate, and the impedance plot is being obtained. So in overview, as I mentioned, in this antimony sulfoiodide, we have tested with aqueous based sodium hydroxide, and also ionic liquid based system with a wider window from -3 to +3 with a lower equivalent like series resistance or the solution resistance. So next I'll be moving on towards solid state devices. So the next 3 will be focusing on solid state device. So the liquid and solid, as you all know, the difference is with the choice of electrolytes. If your electrolyte is liquid, it's a liquid based system. If your electrolyte is like quasi solid, it's a quasi solid system, or a very solid system, it's a solid. If your electrolyte is solid, completely solid, then it's solid state supercapacitors, or like quasi solid state supercapacitors. So now it's like ionogel, so which means a quasi-solid supercapacitor. So this will be focusing on wearable applications. So since we are like focusing on wearable applications, our choice of substrate was carbon cloth, and we have done the electrochemical deposition, and which turned out to be aligned T nanorods, so which are called as tellurine or the methylene series, and we have fabricated with the like tellurine on CC with ionogel. So the variable supercapacitor we have fabricated using TECC with high capacitance of like 235.6 farad per gram with energy density of 73, and the capacitance retention was over 10,000 cycles. Actually, the high power density of 15,000 watt per kilogram was achieved. So comparatively, in other systems, we have got a higher power density in terms using the methylene series. And we have also tested the self-powered system with integration with solar cell, and the energy is being stored with our supercapacitor, what we have done in our lab. So the physicochemical analysis, and this in slide 28, the figure A shows the deposition profile, electrochemical deposition profile of tellurine on the carbon cloth surface, and the XRD, which shows the difference between the deposited carbon cloth and deposited with and without, like the carbon cloth with tellurine and without the tellurine, and the Raman analysis, which showed a few layered structures, and also the XPS, which shows the TE state. So you can see the metal state of TE0, which is called as metallines. So this is the morphological analysis, where you can see, since it's on the carbon cloth, the C and T is being visible. So the electrochemical analysis of tellurine carbon cloth variable supercapacitors. We have analyzed the cyclic voltammetry and the dependence. Since it's wearable devices, the bend tests are like very essential to understand how electrodes are over the surface of CC, I mean the carbon cloth. So normal and bend state, we have studied the electrochemical analysis, and the D shows the Nyquist plot and the Bode phase angle plot, and this one shows the aerial capacitance and with dependence of that of the frequency. So in slide 31, here we have studied the charge discharge and also the self discharge analysis in order to understand the shelf life of our fabricated supercapacitor. So the first one is the galvanostatic charge discharge analysis. So here the dependence on the capacitance, the aerial as well as the gravimetric capacitance in terms of current is being studied. And here the next shows the self discharge analysis. Self discharge analysis of the TECC WSC. So where you can see the self discharge is something like what to understand the shelf life and how far your supercapacitor would be possible for commercialization and things like that. So self-discharge is very important point when you're going towards commercialization. So here, as I told, these are all like extrinsic self-powered systems, where in slide 32, figure A shows the Ragon plot of tellurine on carbon cloth variable supercapacitor. There's a solid device. If you can see in the figure B of 32 slide, you can see the left side, you have a solar cell, and in between you have your tellurine carbon cloth device. So since it's flexible, we tested for the normal and band condition. And once the solar cell is charged, so next you can see the C figure, the light is off and the display starts to work with the storage devices like what we have tested. So though we have used a quasi-solid device, it was able to sustain for a longer period duration, or the power generated with the solar cell is being effectively stored in the tellurine-based supercapacitors. So in overview of this tellurine CC-based, the operating voltage window was like 1.5 volt with the ionogel and high capacitance and energy density, and the power density is 15,000 watt per kg. So the self-discharge analysis is very important, and with the self-discharge analysis, we can understand the mechanism, or like why there is a self-discharge. Is it due to ohmic leakage or the diffusion control pathways or the charge distribution phenomena? And we have tested it as a proof of concept. We have fabricated this and we have harvested the solar cell and tested for the storage with our supercapacitor device. So the next part will be quasi-solid Nafion-based TENG. TENG is triboelectric nano generator. So that is being used as a harvester, and the micro supercapacitor is being used to store the generated energy. This is also a wearable device, and it's an extrinsic device. So the Nafion-based self-powered system, as I told before, all the extrinsic self-powered systems need a power management circuit or a module in order to convert the AC generated from the harvester to store in your storage device. So here, if you see the Nafion-based TENG, where the current collectors are aluminum, aluminum as current collectors, Kapton and Nafion as a positive and negative layer. So once the harvested, like with a mechanical energy being given, your harvested energy is being rectified using a rectifier circuit, and then we have stored it in a microcapacitor, so carbon-based microcapacitor with the Nafion-based gel. So we have utilized Nafion for triboelectric nanogenerator harvesting, and for the electrode and the supercapacitor, what we have done is like we have taken a Kapton tape and we have reduced with the laser irradiation. We have changed the Kapton into carbon-based micro supercapacitor, and we have used Nafion-based electrolyte, and then dried, and then we have analyzed the microcapacitor, and then we have combined it with the external circuit. So these are the analysis of Nafion, and there's a Raman analysis of Raman spectrum analysis with a 34 slide and D figure where shows the carbon D and G band. So this is the triboelectric energy harvester output for the device. So as I told previously, the Nafion-based tank, the voltage and the current output has been measured at different accelerations from 0.1 till 5 year measured. So after a certain acceleration of the force being given, your generator starts to behave where in a solid system like Nafion, it takes a larger time for your ions to turn back to a normal state. All will be in excited state. So it will take a bit more time to come to a normal state. So that's where the relaxation time plays a role in your harvester and the conversion part with your storage. So in Nafion-based tank device, so this is the voltage versus time with the rectified voltage output in slide 36 figure A. You can see the rectified output, and with a different commercial capacitor we have charged, and this is the cyclic stability over 3000 seconds. So now comes, so the harvester part is done. Since we have fabricated in the previous analysis of the studies, we have utilized it with the commercial solar cell. So now we have made a generator with a biomechanical waste energy with a tank, and then we have harvested with a Nafion-based tank and stored in Kapton-derived carbon-based micro supercapacitor. So if you see as the standard protocols for measuring the supercapacitor is being done, the cyclic voltammogram, the galvanostatic charge discharge, and since it's a microcapacitor, we have been focusing on the length capacitance, and also the dragon plot and the retention over a cycle is being studied. So once if you're testing, once your harvester is done and your storage is done, next is the integration part with that of harvester to that of storage with the power management circuit. So it's a solid state system. Nafion is a solid state proton conducting electrolyte as well. So that property we were trying to incorporate in the self-powered cells or the self-powered supercapacitor cells. So in extrinsic as well as in intrinsic, we have studied in our lab. So once there is a change in acceleration with the harvesting, once the storage is done and with it's all being connected as shown in slide 38 figure A, the harvester, the rectifier circuit, and then your micro supercapacitor, we were able to charge around 600 millivolt at 2 meter per second square acceleration. When that much force is given, we were able to store with this system once without any electrical supply, only with the mechanical energy being given at an acceleration of 2 milli per second squared. We were able to store around 620 millivolt, around approximately 600 millivolt we were able to store with this extrinsic self-powered system. So in summary, here in this system, we have studied the Nafion-based PENG as well as the Nafion-based liquid electrolyte for gel-based electrolyte for supercapacitor, micro supercapacitor. And approximately, we are able to charge 600 millivolt in 620 seconds without any electrical supply, only with the waste biomechanical energy. So now our focus will be on these are like as discussed previously, the waste biomechanical energy have a lesser, or in terms I can say for low power applications. If you're going for high power applications, there is like where our batteries in nowadays, like you can see all are driving towards electric vehicles. And as I stated in the introduction part, the electric vehicles which are being hybrid, where you can use it in both ways. It's a hybrid vehicle, new hybrid vehicles. When once you apply a brake, ma'am, can you go to slide 44? I hope you're seeing the slide. For the regenerative braking system or the deceleration energy, what we have tried as a prototype is like, before a battery pack, we are placing a supercapacitor. We are placing a supercapacitor. Like what we have done this time is like graphene-based supercapacitor. So once the brake is applied, the motor, what we are showing here is the electric vehicles motor or your car's motor. Once the brake is applied in acceleration mode, it's in kinetic energy. So once your brake is applied, the kinetic energy is being stopped. So that kinetic energy reversal will directly hit your battery pack, which cause a deterioration in your battery life. So once the supercapacitor is implied between the battery pack and your braking system, the supercapacitor, being a high power density device, it observes, or like it can retain, or it can, with a fraction of it, due to the higher high power density property of supercapacitor, it will capture the energy at a very faster rate than battery, and it stores for a while and then it gives to the battery. So this is what we are looking in high power applications like cars and vehicles. If you're going for low power applications like wearable devices and those, we were looking for waste biomechanical energy. This is also a waste energy, though it's not a waste biomechanical energy, but still it's a waste energy which we are trapping into the supercapacitor and utilizing it at a later stage. So here we have made a graphene supercapacitor with a 3 volt of operating window voltage window and device capacitance of 35.96 farad per gram, energy density and power density over a long cycle for 10,000 cycle. And we've also tested for wide temperature operation, since the supercapacitor has to withstand the temperature when it is being placed in the car or vehicles, wherever it is being placed. So as I told before, wherever your application is and what is your need and what are you working on, choose wisely the electrode and the electrolyte in such a way that suits your applications, or like such a roadmap or thing is needed when you start your work. So the additional use of a graphene supercapacitor as a primary source to store the regenerative braking or deceleration, which acts as an auxiliary source in terms of with the combination of battery. Since as I mentioned previously, if you see, once your graphene supercapacitor is placed in between the battery and your deceleration motor, the capture of energy is there in the graphene supercapacitor. It doesn't actually, supercapacitors does not work alone. It cannot stand alone because of high power density, which is an advantage as well as disadvantage, which means it can capture the energy at a faster rate, but it discharges at a same faster rate. So you need a battery pack. So in order to save the battery, you can use a supercapacitor in electric vehicles. So the electrochemical analysis of the supercapacitors with graphene supercapacitors is being done. And as I told before, the standard protocols are being followed to analyze the performance of the supercapacitor prepared. And the temperature dependent study is much needed when we are keeping it in electric vehicles. And so this is a temperature dependent study. You can see we have studied from -15 degrees Celsius until 80 degrees Celsius, how the cyclic voltammetry performance or cyclic voltammogram of the supercapacitor is being varied, and the capacitor retention with temperature, and the temperature dependent Nyquist plot, and charge transfer resistance, how it's being affected with the role of temperature. When there is a role of temperature, the choice of your electrolyte should be matched with being working in all the temperatures of what we are going to use. So for always a supercapacitor, the synergetic effect of electrode and electrolyte is needed for a better and higher performance. So the regenerative braking analysis is an auxiliary source. As I told, once your battery, like we have tested a prototype where once the battery is, we have placed a battery, the slide number 48, figure 31A. So when the acceleration is off, when you have only a battery, it stores for 40 seconds, for instance. Once if you use a supercapacitor, it can store up to 7 voltage charge, and then it discharges. So this is what it happens when you use a supercapacitor as an auxiliary source. And figure B shows the break and release, like on and off state, like how it is being varied. Point 6 volt, which is very huge when we are comparing with the low power applications, but still 1 volt or 2.3 volt is a very decent deal to obtain when a supercapacitor is placed, and it's also going to save the life of the battery. So in figure E, the brake and the acceleration. Once brake is applied, the supercapacitor was able to store 1.8 volt, depending on your acceleration again. Depending on the acceleration, it's 2 volt or 2.5 volt is being determined. So in acceleration, in figure F, you can see the acceleration and the deceleration energy, how it's being, the role being played by a supercapacitor. So in chapter 6, like we have seen in summary, the temperature dependent analysis of graphene, and their application in EVs is auxiliary power source, and acceleration and effective storage for regenerative and deceleration energy from the EVs. So finally, the proof of concept of utilizing graphene supercapacitor towards portable electronics and electric vehicles is being demonstrated. So these experimental studies highlight the graphene supercapacitor as auxiliary power source in combination with battery, and it acts as a prime source to store the energy generated during braking and deceleration condition. So next is like the self-charging supercapacitor power cell, where here we are not going to go for any external power management circuit. It's a single device which is going to harvest and store energy. So this is called a self-charging supercapacitor power cell. The previous, which are extrinsic, are called as self-powered systems or self-powered cell. So the self-charging supercapacitor power cell, it's a single cell. The supercapacitor electrodes and the piezoelectrolyte film. Or actually, without electricity, you're going to harvest and store with the same device. The configuration is like graphene electrodes and with a piezoelectrolyte film. So the waste biomechanical energy has to be utilized. So the generator, which we have seen previously, was like Nafion separate generator, and now it's like intrinsic cell. Inside the cell, we are using PVDF with a phosphotungstic acid is proton conducting electrolyte as well for the supercapacitor, and also a harvester with for the piezo. So here, the proton conducting based solid electrolyte, piezoelectric PVDF hybrids, where that's used as a supercapacitor as well as the harvester. So that's the overall view of this work. So the piezoelectrochemical energy conversion process is being studied in this work. As I told, the graphene nanosheets being used as the electrolyte, and PVDF phosphotungstic acid, which is a proton conducting electrolyte, is used as the harvester as well as a storage electrolyte. So the physicochemical characterization of graphene nanosheets, which shows we have reduced through thermal reduction. So the GO and how the graphene is being reduced, being observed through FTR and XRD and XPS, and through HRTM we have observed the few layered structures of graphene is being obtained. So this is the Raman mapping of graphene sheets, slide number 54. So this is the 3D map of D and G bands of the graphene sheets which is being produced or like synthesized. So the D band intensity and the G band intensity are being shown in B and C, and ID by IG ratio maps shown in D, which shows the even distribution of D and G maps. That means the graphene is being grown over like in a common surface, or it's being uniformly distributed over the surface, or it's being synthesized. The D and G band ratio intensity maps is being shown. So for the preparation of the phosphotungstic acid with PVDF, so this is what an electrolyte as well as the harvester. This is going to be the electrolyte as well as the harvester. We're done with the solution casting method. In B, you can see it's, the color change is due to the addition of electrolyte, which is phosphotungstic acid. And C and D is the same image of the generated or the synthesized film. So you can see the pores being obtained. This is the elemental analysis of the map of your synthesized membrane or the freestanding membrane, where you can see phosphorus, tungsten, oxygen, carbon, and fluorine. Fluorine is from the PVDF chains. And phosphotungstic acid is H3PW12O40. So where you have abundant protons to hop over H3, you'll have free H to hop over. So for the film state, we have studied the role of addition of PTA into the PVDF matrix. So this is the Raman mapping of PTA, phosphotungstic acid, with PVDF matrix. So here, if you see, what we are trying to explain in this Raman mapping is like when you use two or like a composite, you can see here this blends of PTA and PVDF is being uniformly distributed all over the film. This is what we are trying to explain with all these maps. So the first one is 3D Raman array. The second one is peak position of beta PVDF. Beta PVDF is something which is the electroactive phase of PVDF. Once if you want to go for a generator part, the electroactive phase is very, very important. So if your PVDF phase is electroactive, then only you can do a generator, or it could be used in generation, or else you couldn't make it for generation, or it will be like it's not electroactive phase. So the beta phase is being obtained, and the peak position of WO, and where you can see the proper blend of phosphotungstic acid and PVDF is observed without disturbing the electroactive phase of PVDF. So if you see the intensity map of PVDF and the intensity map of WO, you can understand like how it is being distributed with the ratio of intensity of W versus O is for phosphotungstic acid and beta phase is for the PVDF. It is being uniformly distributed all over the surface on the freestanding film of phosphotungstic acid with PVDF. So here we are explaining like the ionic conductivity, the change in ionic conductivity with and without addition of PTA with PVDF. And also we have studied the ionic conductivity, and this is your plots of figure slide 59, and here you can see C figure which shows the current, and D figure which shows the voltage output with PVDF and without without PTA with PVDF. So if you see, there's an improvement in your voltage and current once the phosphotungstic acid is added, which means the phosphotungstic acid addition does not reduce the electroactive phase of PVDF, but still it increases the output because of free ion moments being obtained or being observed in your proton conducting electrolyte membrane. So the peak voltage with the dependence of force is studied, and also over the cycle, like we have studied for 600 seconds, more than 600 seconds actually. And we have also studied the electrochemical analysis of graphene self-charging supercapacitor power cell, the solid electrolyte. As I told, those are quasi-solid systems where the minimal layer of phosphotungstic acid and PVDF is being used to harvest and store with an interfacial layer of PTA and PVDF. So the cyclic voltammetry, the charge discharge analysis, and dependence, the specific capacitance dependence on scan rate and current is being observed. The Ragun plot which shows a higher and better performance, and it is being retention. The capacitance is being retention over 5,000 cycles is being studied. So next is like the self-charging performance of. So this is what I was explaining, the next generation electrochemical energy storage devices or supercapacitors. The self-charging performance of graphene supercapacitors with this. As I told, if you slide number 61, figure 27C, if you see, that is the structure of the device what we have fabricated. So you have electrodes, the current collector, or because we are going towards flexible, you're tested with carbon cloth. So carbon cloth is current collector and graphene coated over carbon cloth, and PTA, PVDF as a separator and electrolyte. So once the force is applied, if you see the second figure in figure 27, I mean like in C subset figures, I'm explaining the mechanism of piezoelectrochemical process, what's happening in a cell of integrated energy systems or like an intrinsic cell. So when there is no force being applied, there are no charges or the piezo potential generated at the device. Once the force is applied, there are piezo potential being generated at the separator. So once the piezo potential is generated in the separator, it is being transferred to the electrodes. And once the charge neutrality is being obtained, there will be redistribution of charges. Once again the force is released, then it tries to come to its equilibrium state at a faster rate, and then it comes to a relaxed state. That is how, without any power management circuit or the module, we are able to harvest and store in a single device the waste biomechanical energy. So you can charge, we have charged up to 160, approximately 160 millivolt in 210 seconds, in 210 seconds. So this is for the continuation of 10 repetitive cycles in order to show the stability of the device is being obtained, and we are able to charge for 10 repetitive cycles and even more. So in summary, here we have shown the homogeneous distribution of PTA and PVDF polymer matrix, and we have utilized the graphene self-charging supercapacitor power cell device fabricated using PTA PVDF piezoelectrolyte film, which delivered a better aerial capacitance and energy density, and self-charged up to 110 millivolt. So these are now in the lab scale production and in research, which is very much needed towards the realistic approaches in the near future, hopefully, once the entire mechanism is understood. So the conversion efficiency should be sorted in a very different way. Hence, then it could be used in commercialization. So in summary, overall summary, today we have seen why there is a need for supercapacitor, why do we need an electrochemical energy storage device, and in that, what is the importance of supercapacitor, and how your performance of supercapacitor could be changed with the choice of electrode and electrolyte. And in the integrated system, we have seen tellurine-based extrinsic self-charging power system with tellurine, naphthalene, and deceleration with a graphene supercapacitor, and the intrinsic with the phosphotungstic acid and PVDF as a multifunctional applications. So in conclusion, as I mentioned before, that's what the same with the quantitative values, selected publications, and acknowledgements. I'd like to thank my professor, Mr. Kim Sanjay, and my members of Nanometals and System Laboratory, and Jeju National University and NRF for the fund for my project, and Brain Korea, and also the instrumentation facility. So it's time for questions. If you have any questions, please. Okay. Thank you, ma'am. Thank you so much. Thank you for the opportunity. Thank you, ma'am. Yes, ma'am.
Yes, ma'am. Is visible, ma'am?
Good afternoon, everyone. Myself Saranyavi. I am from DG Vaishnava College, studying MSc with the second year. Our poster topic is about a photocategory performance of third order NLO active. So our poster topic is about a photocatalytic performance of third order NLO active nickel oxide cadmium oxide green synthesized using CDM guajava leaf extract. We know that dye industries uh, release wastewater which contain organic pollutants which will affect the aqua organisms, and animals drinks that water will also to get affected. So we prepared a nanocomposite compound named nickel oxide cadmium oxide green synthesis.
Yes, ma'am. Okay, ma'am.
So we have prepared a green synthesized nickel oxide cadmium oxide nanocomposite using CDM guajava leaf extract. The phytochemicals present in this CDM guajava leaf extract has a potential ability to reduce the dye molecules present in the rhodamine dye product. So when we took a photocatalyst test means in water purification, a catalyst and a visible light is used to degrade the dye molecules present in the compound. So when we took a photocatalyst test, it is shown that synthesized nickel oxide cadmium oxide has removed effectively the rhodamine dye under visible light. And after 90 minutes of irradiation of light, this nickel oxide cadmium oxide nanocomposite has removed 86% of the dye molecules. So my friend Subhasti will tell the preparation techniques of the nickel oxide cadmium oxide nanocomposite.
Myself Subhasti, DG Vaishnava, second MSc Physics. Nickel chloride plus cadmium chloride in 120 ml of ionization water and 30 ml of guajava leaf extract. The solution was stirring for 2 hours and gaining for 2 hours. Precipitate result from the two solution was separated, washed with water and heated at 400 degrees Celsius for 1 hour and then crushed well to form nickel oxide, cadmium oxide, nanocomposite.
And a photocatalyst activity was performed using rhodamine dye. Rhodamine dye is a carcinogenic dye, and we took this dye whether this green synthesis nickel oxide cadmium oxide can degrade that dye. So for this test, we are taking the 10 ml of the green synthesized nanocomposite catalyst, and we added the 100 ml of aqua solution. So after achieving the equilibrium, that is absorption and resorption, this dye solution along with the catalyst separated and exposed to the visible light. So after regular intervals of time, 2 ml of this solution were separated, and the absorbance was recorded, and the value is found to be lambda is equal to 554 nanometer in the square. And we have done the results and discussion. First test we have taken is GCMS analysis. It is nothing but the gas chromatography mass spectrometry. Is an instrument used to measure the chemical constituent present in the sample. So we are taking the CDM guajava leaf extract, and we are determining the phytochemicals present in this.
So the phytochemicals present in this CDM guajava leaf extract are caryophyllene, amacystol, ecosane, beta-cystol, and gamma-cystol, and 5-alpha reductase. So these are the secondary metabolites responsible for the stabilization of the nickel oxide, cadmium oxide, and a composite.
XRD, diffraction peak related to cubic structure, cadmium oxide represented by the symbol were observed in XRD pattern. In the figure, we can observe JCPDS peak matching our sample figure. XR and then same analysis, same image with a different scale of the given synthesis. We can confirm nano needle along with irregular shape gain in our sample. Nano rod along with bended spherical scales are visible in the figure. It is the same analysis. And then FTIR spectrum of green synthesis, nickel oxide, cadmium oxide, nano composite. The functional group are present in our sample. Approximately 3,558 to 2,980 is water molecular, 1,560 is double bond O, 941 is CH bond, and 765 is NH bond, 810 is cadmium oxide, and then 520 is nickel oxide. And analysis in FTR.
Yes. Can you please move on to your results and discussion?
Yes, ma'am. And using laser scan, we can find the NLO refractive index was found to be 5.24 10 power minus 4 Newton meter square per watt. So what a laser scan means, we are taking the India laser and we are passing the Z direction, and we are finding the non-linear refractive index value was found to be 5.24. I'm concluding my topic is we have prepared a nanocomposite compound, nickel oxide, cadmium oxide nanocomposite using green synthesis. So which is eco-friendly, and it is proved that using the photocatalyst is 86% of dye molecules were degraded using this nickel oxide, cadmium oxide nanocomposite. So we are using the green synthesis product, so it will be eco-friendly, and it is degrading the dye molecules also.
That's it, ma'am.
Okay, can you just tell the significance of your study?
Yes, ma'am. First significance is it's eco-friendly, ma'am. It is non-pollutant, and we are degrading the dye molecules also. And this NLO non-linear optics, this nickel oxide, cadmium oxide is used in the metal oxide industries also.
Okay, ma. Okay, good. Thank you.
Thank you, ma'am.
Yes, ma'am. I'm Renuka Devi. I'm the second author of this paper, ma'am. I'm going to. Yes, ma'am. Yes, ma'am. Ma'am, whether my screen is visible, ma'am? Yes, ma'am. Good afternoon, everyone. I'm Renuka Devi, working as a project student under the guidance of Dr. R. Ilangovan, National Center for Nanoscience and Nanotechnology, and my project is entitled as Enhancing the Antioxidant, Antidiabetic and Antibacterial Properties of Curcumin Coated Zinc Oxide Nanoparticles, where the figure 1 shows us synthesis of curcumin zinc oxide. Before going to the synthesis introduction, the body's defense mechanism often require support in preventing effective of oxidative stress. Diabetes mellitus is a complex metabolic disease characterized by high glucose level due to either insufficient insulin or insulin resistance. To overcome all this complication, we have synthesized curcumin coated zinc oxide nanoparticles. Figure 1 shows us the synthesis of curcumin coated zinc oxide particles. Zinc nitrate is dissolved in distilled water and heated up to 80 degrees Celsius. Curcumin is taken and dissolved in acetone, and this curcumin dissolved acetone is added to zinc nitrate solution and stirred for further hours, and then NaOH is added to that solution, and we can obtain a precipitate solution. This is centrifuged for further hours and nanoparticles are synthesized. Figure 2 shows us the UV spectra of prepared samples, where the peak appeared at 430 nanometer is due to curcumin, and the peak while appeared at 2 places at figure 2, which is due to curcumin and zinc oxide, where our prepared samples absorb UV radiations. Figure 3 shows the XRD spectra of prepared samples. To determine the crystalline phase of prepared curcumin coated zinc oxide, XRD characterized was carried out. Several peaks were observed for curcumin zinc oxide nanoparticles. Figure 4 shows the photoluminescence study of prepared samples. The excitation wavelength range is between 400 to 700 nanometer. PL is carried for both the curcumin and curcumin coated zinc oxide nanoparticles, where 450 nanometer is for curcumin coated zinc oxide nanoparticles, and the peak appeared 543 is due to pure curcumin. The fifth figure shows the FTR spectra of the prepared samples. FTR is carried out in order to determine the presence of functional groups. The peak appeared at 1445 is due to presence of 2 methyl groups. The peak appeared at 427 is due to stretching vibration of zinc oxide. The peak appeared at 3402 is due to OH group of zinc oxide. The peak appeared at 1645 is due to bending vibration of OH group. And the peak appeared 1362 is due to angular deformation of ammonium ion.
Please move on to the conclusion, ma'am.
Yes, ma'am. Conclusion. The antioxidant properties and antimicrobial assays are carried for the prepared samples, so that I conclude that the prepared curcumin coated zinc oxide nanoparticle shows photoluminescence properties. From the fluorescence, the figure 8 shows the fluorescence microscope images. We conclude that it can be applied in many biomedical applications such as bioimaging and cancer treatment. The references are displayed below. Thank you.
What type of sample you procured? Is it a pure sample, or how did you extract? Any information on that?
It is pure sample.
How did you extract it?
Sorry, ma'am, I can't get your question now.
No. How did you get the sample? Is it purely? Is it available, or did you extract from any other compound like that? I'm asking.
Extract, ma'am. Extract.
How?
From SRL, ma'am. From SRL chemicals, ma'am.
Tell me the procedure. You extracted, huh?
Yes, ma'am.
Tell me the procedure.
Yes, ma'am. The zinc nitrate is added to distilled water, ma'am.
Okay.
Then it is heated, ma'am. In another step, curcumin, pure curcumin is added to acetone, ma'am, and it is stirred, ma'am. The curcumin solution is added to zinc nitrate, ma'am.
And under what temperature you performed all these things?
Ma'am, at room temperature, ma'am.
At room temperature.
Yes, ma'am.
Okay. Thank you. Good.
Thank you, ma'am. Yes. Yes, ma'am. Ma'am, can you hear me, ma'am? Yeah, ma'am. Yeah, ma'am. I'm sharing it, ma'am. Is it visible, ma'am? Okay. Good afternoon to everyone. Myself, Tarini. I am a research scholar in SRM Institute of Science and Technology, Katangalatur. So now I am presenting my work, which is hydrothermally treated tungsten oxide as an effective cathode for deep cyclable
aqueous zinc-ion battery. So first and foremost, I'll tell you why we have to go for zinc-ion battery. So as of now, in electric vehicles and all, the most common battery type which is used is lithium-ion batteries. But as we all know, there are a lot of problems associated with lithium-ion batteries, even though their output is very good. So some of the common problems are, first and foremost, their cost. That is the making cost of the battery, and the next one is the operation safety. That is, whenever there is a fire accident happening in EV vehicles, it will be mostly associated with link.
Excuse me, madam, please
yes,
explain your work, please.
Yes, okay. So so that's why I've gone for a zinc-ion battery. It is eco-friendly. So moving on to the experimental part, I've taken sodium tungstate and dextrose, and then I've autoclaved at 200 degrees Celsius. After that, I've gone for high temperature annealing so that we'll get a good crystalline natured sample. So after that, I've gone for structural analysis. The first and foremost, XRD analysis, which confirmed the characteristic peaks at 23, 28, 24, confirmed the presence of tungsten oxide, and the high intense peak represents that the crystallinity is very good for the obtained WO3. The structure is monoclinic structure. And then to further analyze it to the shape, I have gone for SEM analysis, that is scanning electron microscope analysis. From the analysis, you can see that I have got a very good cubic structure. And then I've also performed EDAX analysis, which again confirmed the presence of tungsten and oxygen. So these are all some of the structural analysis. And then to confirm the bonding, I've gone for micro-Raman analysis as well. So you can see that the characteristic peaks at 200, 300, 710 and 804 confirms the stretching of tungsten oxide, that is W bonded with O and W. So this again confirms the stretching presence in the WO3 sample. So these are some of the structural and morphological analysis I've carried out to confirm the presence of WO3. So moving on to my battery application, I've performed the electrochemical studies. So here I have taken a Swedge-Lock setup where I have used zinc as my anode, and then zinc's the normal separator. On top of that, I have used 1 molar zinc sulfate solution, and the cathode material. The cathode material is the active material which I have synthesized, that is WO3 tungsten oxide material. I have formed a slurry with the help of active carbon black and the PVDF, which is a binding polymer, and then I have formed a slurry and coated it on top of a stainless steel foil, and then I have dried it. So that is my active material that I have used as the cathode. So I have formed a setup using the Swedge-Lock setup where zinc is an anode separator. On top of that, I have dropped 1 mole zinc sulfate solution, followed by it my active material which acts as the cathode. So this study, I have done it in the room temperature setup. So I have used Aurigalis' electrochemical workstation. So first and foremost, I have done the CV analysis. So the CV analysis, clearly the peaks at 0.7 and for oxidation peak, and also the reduction peaks at 0.4 clearly indicates the presence of tungsten oxide in the sample. And I have carried out my work in 5 different scan rates, and followed by it, in order to know what is the specific capacity of the given battery for my material, I have done it in different current density. For the current density of 0.1 ampere in gram inverse, I've got a specific capacity of around 12 milliampere hour gram inverse, and I have done this in order to check the stability, whether the material is stable or not. I've done up to 50 cycles. Until 50 cycles at different scan rates, the specific capacity of the given sample was good. So hereby I conclude that.
Yeah, please do the conclusion.
Yeah. Hereby, I conclude that I have synthesized a cubic structure, high crystalline cubic structure tungsten oxide, which is very stable at different scan rates, and at a very even after 50 cycles, the stability of the material was not affected. And in order to support my conclusion, I have carried out XRD, a lot of structural studies and micro-Raman studies, and to prove the stability and the output of the given battery, I have also carried out electrochemical studies. So that's my work.
Okay, good. Can you just brief about your literature survey done to choose your topic today? Because and another question is how your this battery is going to be very innovative or very useful compared to the conventional existing batteries.
Yeah, okay, ma'am. So first, answering your first question, why I have gone for tungsten oxide is that, so I am working on transition metals, ma'am. So why I have chosen this transition metal-based oxides is that, if you observe the 3D orbital of this given material, they resemble very closely to that of the noble metals like platinum. So you all know that the platinum materials, they are very good electrocatalysts, but the main problem associated with them is their cost. So in order to avoid the cost factor, what I've done is I've chosen another material which has a very close resemblance to that of the platinum based materials. So if you take that 3D
I just want to know, not why, that is what type of survey you did. Did you do any survey on the existing batteries and then came out to the conclusion?
Yeah,
like,
I have. I have done a literature survey. After that, only I've gone for this synthesis.
Okay, so whatever you cited was beneficial, so you chose this.
Yeah, yes, ma'am. So moving on to your second question. What is the importance of my work is as of now, the zinc ion batteries, we can't scale it up to the EV vehicle stage, but still there are other battery applications for medium scale applications, like where the output is not that much higher compared to that of the EVs. So I am just saying that instead of going for a very higher scale, we can even start from lower scale, where the output voltage required is very minimum, so that in that sector we can replace lithium ion batteries with zinc ion batteries. So in the future, if we keep on researching, it will appear like we can scale it up to EVs level.
Okay, you did all the studies at room temperature, right? So do you have any idea what is the temperature that your battery can withstand? The maximum maybe.
Like actually,
have you done anything survey like that? Have you done any?
Like you're asking whether I have increased the temperature and I have checked it out.
Yes.
No, ma'am. I haven't done it because my annealing temperature itself is very high and the crystallinity is very good. So I think I am sure that according to literature survey, it will stand up to 80 degrees Celsius, ma'am.
Okay. Good. Thank you.
Yeah. Okay. Yeah. Thank you. Yes, ma'am.
Harini is here. Huh? Otherwise, move on to the next one.
Yes, ma'am. We are here. Yes, ma'am. We'll present it. Yes, ma'am.
Or else we can move to the next one. If she's having any network issues, we'll move on to the next one, ma'am.
Yes, ma'am.
Yes, ma'am. Hello. Okay, ma'am. Hello. Can you hear me, ma'am? Can you
please share your screen?
Okay, one second. Good afternoon, everyone. I'm Blessy Rebecca from SRM University. I'm doing PhD under the guidance of Ajay Rokesh, sir. So I'm going to present about the synthesis of graphene and ZIF-8 nanocomposite for the non-enzymatic detection of glucose. So we all know diabetes is one of the leading diseases in the world. So there are constantly increase in the diabetic persons in the world. So we require the continuous monitoring of glucose. So there are many commercial glucose sensors available. So, but the commercial sensors are based on the.
Please move on to your work, ma, please.
Okay, ma'am. So we have decided to develop a sensor based on the non-enzymatic detection. So I have taken a ZIF-8, which is a metal organic framework. I have prepared ZIF-8 from zinc nitrate source and methylimidazole. After stirring and aging, and after centrifugation and washing drying, I have prepared a ZIF-8. And for comparison, I have prepared ZIF-8 composite with graphene. So I have compare the metal organic framework, and to increase it electrical conductivity, I have added graphene also. So to move into the material characterization, the first one is XRD. From the XRD, we have concluded that the ZIF-8 particles are prepared, and after adding graphene, there won't be many significant peaks, because the addition of composition of graphene is lower to that of the ZIF-8. And for further characterization, I have taken the FTIR. So from the FTIR, we can see the bonds between the zinc oxide and imidazole frameworks, and after adding graphene, we can see the bonds of the graphene, like C double bond C and CO bonds. And further characterization, I have taken a UV analysis. From that UV, we can see clearly see the absorption bands shifting. So after moving on to the morphological analysis, the D represents the SEM images of the ZIF-8. From that SEM image, we can see the uniform formation of the ZIF-8 composites. After adding graphene, we can see that the ZIF-8 materials particles are clearly distributed on the graphene surface. And the further EDAX analysis shows that the formation of graphene and ZIF-8 composites. And after forming the composites and the pure material metal organic framework, I have done electrochemical analysis. So I have done the electrochemical analysis using the 3 electrosystems, which I used my material ZIF-8 and ZIF-8 graphene composite as a working electrode, which is coated on the pencil graphite electrode, and I have used AgCl as a reference electrode and platinum as a counter electrode, and PBS as an electrolyte to detect the glucose concentration. So the A image clearly shows that after adding glucose, we can see that there is an increase in the current, which shows that the prepared material, both the ZIF-8 and the ZIF-8 graphene composites, clearly shows I have a sensitivity to the glucose. And after that, I have performed different concentrations for ZIF-8 and ZIF-8 composites. For the B image shows that the different concentrations of the ZIF-8 material. I have added from 0 millimolar and to 10 millimolar. So we can see there is a clear increase in the current rate. And after adding for ZIF-8 composite with graphene composite, we can clearly see there is an increase in the current rate. So
okay, move on to the conclusion.
From this, we can conclude that both ZIF-8 and ZIF-8 graphene composites clearly shows the sensitivity for a glucose. After adding graphene, which is a carbon-based material, I have added to increase the electrical conductivity. It shows there is a higher increased current rate in the sensing. That's all.
Okay. Can you suggest any other replacement for graphene in your study?
I have synthesized graphene from a biomass source, ma'am. So it formed layer structures, and from the biomass we have done carbonization, and after that activation using some chemicals.
Instead of graphene, what else can be added? Have you tried?
No, ma'am. Until now, I didn't try. We can add metals, particles, or metal oxides like that, ma'am. metal particles provide good electrical conductivity. Instead of carbon-based materials, we can add metal particles.
How it will change the result? Any idea?
Yes, ma'am. It will increase the conductivity means plus metal particles also provide electrocatalytic activity means, so it will increase the sensitivity of the glucose, ma'am.
Okay, thank you.
Thank you.
Yes, ma'am. Yes, ma'am. Ma'am, is my screen visible? Ma'am, our poster is based upon studies of GD doped retinal nanoparticles by co-precipitation method, ma'am.
Yes, ma'am. Proceed. Tell the work and the conclusion, please.
So the growth of textile and dye industries in recent times took a toll on the purity of water bodies, affecting life due to organic compounds present in them. Zinc oxide is generally examined photocatalyst because it has a non-toxic nature and good electrical, optical, and oxidation resistant properties. As zinc possesses a band gap of 3.2 electron volts, it can absorb only 4% of light, limiting the photocatalytic efficiency of ZNO. Now the procedure, ma'am. For 3%, 2.1511 gram of ZAD was measured and added to beaker, and 1.35408 grams of GD was measured and added to the same beaker. 100 ml of distilled water was poured into it. It was kept in the magnetic stirrer for 30 minutes. Next, 4 grams of NaOH was measured and added to a conical flask. 10 ml of distilled water was added to it and left in the magnetic stirrer for dissolving. After dissolving NaOH and distilled water, it is poured in the washed burette. When half an hour is over, the ZAD plus GD solution is checked with pH paper. Now the NaOH solution is added in drops from burette to ZAD plus GD solution with continuous magnetic stirring. This is done until pH is 11. This is further stirred for 1 hour.
Tell your result and discussion, please.
Okay, ma'am. Ma'am, we sent our powder sample for characterization techniques. We used XRD, UV, and Raman for our studies. For XRD answer, by XRD studies, we were able to observe high degree of crystallinity of sample, ma'am. The HKL planes corresponding to 100002 and 101 peaks were observed, and all these peaks included to prove that we got hexagonal wood-side structure. And while we add dopant, that is GD, there is a shift in the diffraction maxima, and that was increasing when the GD percentage was increased. So next, we go on to UV. Optical studies were done by using UV visible spectroscopy, and we analyzed between the ranges 200 to 800 nanometers, and there is a strong absorption peak from the absorption of the material, and that was found between 355 to 370 nanometers. And we calculated band gap by using Tox plot formula. For pure, our band gap was found to be 3.167 electron volt, and for 3%, 4%, we've included in our poster, which is 3.122 electron volt, 3.144 electron volt, and 3.13 electron volt. Next, we move on to Raman studies. So structural properties were analyzed by using Raman spectroscopic studies, and the
Please
two main peaks.
Conclusion. Please move on to the conclusion.
Yes, ma'am. So metal oxide nanocomposites were synthesized by co-precipitation, and the optical studies were analyzed by UV visible, and the obtained nanocomposite can be employed in various applications such as pollution control due to its antimicrobial properties, energy storage due to its wide band gap energy.
and these are the references that we used for our closed demo. Thank you.
Why did you choose this study?
Ma'am, actually we wanted to do wastewater treatment, ma'am. So for that, we started with pure ZNO, and then we doped with GDA to see whether we find any efficiency, increase in the efficiency of our wastewater treatment, ma'am.
Have you compared anything like that?
No, ma'am.
Have
We
you
are
compared the
yet to do,
efficiency? You are ready to do. Okay. Okay. Thank you.
Yes, ma'am. Thank you, ma'am.
Yes, ma'am. I'm here, ma'am. Ma'am, is that visible? Okay. So good afternoon, everyone. So this is Naveen from SRM Institute of Science and Technology. I'm doing my PhD under Dr. Ajay Rakesh. So my work is based on MaxSpace inks for micro supercapacitors. So I've screen printed MaxSpace inks. So basically, MaxSpace materials are precursors of MX inks, which is similar to graphenes, which are 2D nanomaterials. So here I have synthesized MaxSpace material with simple one-step technique because MaxSpace is very much harder or difficult route to synthesis. It must have to it must need a much more complicated environment like annealing. For annealing, you have to need much more furnace and so the equipment necessary is very much high, but here we have simplified the process. And the next thing is we have made it into an ink and then screen printed it to make a micro supercapacitor. So first of all, we characterized it with XRD, Raman, FTIR, and SEM analysis for basic material characterization. So during the XRD characterization, we could able to see a formation of metal oxides like vanadium oxide and aluminum oxide along with the expected max phase. That is because of the route we have done, because this is a simplified route. So we don't use much more complicated devices, complicated furnaces. So generally they use furnaces with temperatures that going up to 1600 degrees Celsius, whereas we use the minimum temperature, that is the minimum available temperature with normal box temperature.
I think you can just concentrate on your work and the result, please.
Okay. So here with FTIR analysis, we can able to see the metal oxide bondings at around 500 to 1000 centimeter inverse, and whereas we can able to see the carbon-carbon bonding around 2500 to 3000 range, which is confirming the presence of vanadium carbides, and also the Raman spectroscopy confirms the presence of vanadium carbides along with the formation of metal oxides. So going on to the electrochemical studies, so have studied basic electrochemical studies such as cyclic voltammetry, GCD, and EAS, electrical impedance spectroscopy. So during cyclic voltammetry, have the device I have fabricated. This is the device I fabricated. So the device run very much good, and for even at higher scan rates, the device is stable, and for even at 100 millivolts per second scan rate, the device is stable, and the capacity retention is around 85%, and we have achieved around 304 farad per gram capacitance. So this is pretty much higher, and the MaxSpace inks are pretty much unexplored area in this field of micro supercapacitors, and we have tried this thing. So coming to GCD, so GCD is discharge cycles. So here you can see for different current densities. So the charging and discharging has to be faster for supercapacitors. So, and that's the thing we are expected, and we have
please
achieved
move on to the
same.
conclusion, please.
Yeah. So the main thing is during our electrochemical studies, we have revealed that the pseudo-capacitive nature of our material. Pseudo-capacitive nature means the ion intercalation happening. So our material is pretty much good and very good to batteries, ion batteries and ion capacitors such as lithium, sodium, potassium. So it can be used for these purposes. And also the material is binder free. As the title said, the stabilizer free. It doesn't need any binder to bind on substrates. So we can use it for flexible devices, which is very good result we have obtained. So,
okay. Where have you trialed your device? How did you trial your device?
Okay, so we have just studied with these things. And we have connected with the LED. So after charging and discharging, we have connected with the LED. It have glown with minimum intensity, but I haven't posted the picture here.
Okay, thank you.
Yes.
Yes, ma'am. Can you hear me, ma'am? Okay, ma'am. Ma'am, is my slide visible, ma'am? Oh, yes, ma'am. 1 second. Ma'am, I'm unable to share my screen, ma'am. 1 second. Ma'am, I'm unable to share my screen, ma'am. Only 1 second. Just give me a second, ma'am. Yes, ma'am. Okay, ma'am. Yes.
Yes, ma'am. Yes, ma'am. Ma'am, my screen is visible. Greeting to all. My topic is a novel polymer composite with carbon nanoparticle as a photocatalyst. Carbon nanoparticles are used in various fields like medicine, agriculture, and photocatalytic activity, and so on. Among various methods are used to synthesize the carbon nanoparticles. Using the my recent study is using the hydrothermal method, using the banana peel extract lead to the application of the photocatalytic activity. Synthesis of banana peel using the deionized water and grind well, and kept it in the mixture for air oven for about 24 hours at 200 degrees Celsius. A brownish yellow crude solid will obtain then dissolved in distilled water or conductivity water. We can get the solution form of nanoparticles. Then the supernatant liquid will show the fluorescent property. The carbon nanoparticles were confirmed using the UV data and PL data and SEM also. In SEM result, the carbon nanoparticles ranges within the nanometer 1 to 100 nanometer. In UV result, it shows the 287 nanometer, which correlate to the pi to pi star transition band of aromatic. That is carbon-carbon double bond. That is sp2 hybrid orbital, and the n2 pi star is also absorbed in this carbon nanoparticles. And the PH spectra will show was carried out at a different excitation wavelength. The fluorescence spectra of the carbon nanoparticles show the maximum wavelength, 460 nanometer. Carbon nanoparticle at daylight, it does not any color, but under passes UV, it shows the blue region. The blue region under the ranges of 420 to 495, and then the prepared carbon nanoparticles with the polymer is also added to it to prepare the nanocomposite. And also added to the acetone. The mixture was stirred for a magnetic stirrer under the 16 minutes. A viscous polymer layer was obtained, then transferred into the stainless steel,
go to your results,
allowing
please.
for sometimes the polymer film is obtained.
Go to your
My
results,
application
please.
of the carbon nanoparticle is photocatalytic activity. Carbon nanoparticles synthesized from banana peel solid waste as a cheap and abundant precursor will be used to as the photocatalyst to remove the organic pollutants such as methylene blue from water. The summary of this my work is green approach method. It is harmful effect to the other chemical substances, and the biomass of carbon nanoparticles have the excellent water solubility and water compatibility and so on. And it is the good photocatalyst activity.
Yes, conclude, please.
It is used as a good photocatalyst, and it's also used in cancer treatment. That's all.
Okay, where did you carry out these studies? Where did you carry out these studies?
From literature survey.
Literature survey. No, you talked about excitation wavelength, right?
Yes, ma'am.
How many different wavelengths you tried?
Ma'am, under UV, I get 287 nanometer. That
Okay.
excitation layer passes through the PL.
Okay, thank you.
Thank you.
Yes, ma'am. I'll present, ma'am. Okay. Ma'am, is my screen visible, ma'am? Okay, ma'am. Shall I start, ma'am? Sorry for the delay, ma'am. Yeah. Yes, ma'am. I'm B. Kirba Shakti. I'm from National Center for Nanoscience and Nanotechnology. I'm doing my MSc project under the guidance of Dr. T. Prakash. So my work is on the crystallite size effect on nanocalcium tungstate indirect conversion X-ray sensor. So first of all, the need for X-ray sensors is that X-ray imaging is one of the powerful analytical tool which is commonly used as a medical diagnostic technique. We all know that. So why do we need to sense X-rays? Because X-rays are highly ionizing in nature. That means prolonged exposure to X-rays will cause radiation-induced cancer and genetic damage. Therefore, we need to use these X-ray sensors and dosimeters in those labs and also for the patient and for the technician to monitor its effects. So in the first figure, I have shown the values of effective doses used for various medical X-rays. So from this image, you can infer that the lowest dose which is used is for intraoral dental X-rays, which is 0.08 0.008 millisievert. So I have used this dental intraoral machine for my sensing application. So therefore, the sensor I have developed will sense the lowest dose possible. And the material which I have used is calcium tungstate, so which is one of the scintillating material. So there are two types of sensors: direct conversion and indirect conversion. So in the direct conversion, it will want the material sensor will directly convert the X-rays to electrical current, and you can measure it. But in the case of indirect conversion X-ray sensor, the material, a scintillating material will be there. It will convert the X-rays to visible light, and this visible light will be measured by means of any photodetector. For example, like photodiodes or photomultiplier tubes, etc. So in my case, I have used photodiodes for converting the visible light to current. And the scintillating material which I have used is calcium tungstate. So this is the second figure is the attenuation plot for the calcium tungstate, which I have plotted from online source. It is a plot between total attenuation coefficient and the photon energy in kilo electron volt. So here for X-ray source, it is around 70 kilo electron volt, and you can see the total attenuation coefficient of this calcium tungstate at 70 kilo electron volt to be 7.192 centimeter square per gram. So which is actually a very good attenuation coefficient. That means calcium tungstate attenuates, that is absorbs the X-rays. And I have coated this, so I have prepared this calcium tungstate from chemical precipitation method, and I have heat treated it at 4 different temperatures to obtain different sizes. So I have played around with these sizes, and I have obtained 4 different crystallite sizes. So I have coated this nanocalcium tungstate on 4 different photodiodes. So here you can see the digital images, and in the left you can see the X-ray images. So this X-ray images are from a sensor, and this white enhanced light shows that this calcium tungstate attenuates. That means it absorbs. So this is a result, like it shows attenuation.
Yeah, move on to the conclusion, please.
Yes, ma'am. And I also have done characterization techniques to confirm the crystallinity and the phase purity of the sample, XRD and Raman analysis. So the basic application part, I have taken IT measurements using a source meter. So here you can see the first graph is the dark current. That means I have not applied any X-rays. But in the second case, I have passed X-rays at exactly at 40 seconds. So you can see there is a current. So this is X-ray instigated current. That means this current generated due to the X-rays. So I have done this IT measurement for various samples, various crystallite samples, and I have seen that as I decrease the size, the X-ray instigated current becomes more. That means it enhances the sensing ability. So by reducing the sizes to certain nanometer, I can see the sensing ability has been increased.
Yes, please conclude.
And the sensitive, yes, ma'am. And the sensitivity of the sensor can also be calculated from this formula. And from all this, I can conclude that nanocalcium tungstate can be regarded as a promising scintillating material for low dose X-ray sensing applications. And this crystallite grain size effect can also be studied in detail. That's all, ma'am.
Okay. So your sensor, whatever you used in the study, it's an indirect one, right?
Yes, ma'am.
Yeah. So have you thought about, or have you compared anything with the direct conversion method?
Yes, ma'am. Actually, in my lab, they are already working in direct conversion X-ray sensors, ma'am.
Okay. How far you got the result to be significant when compared to that in your study?
Ma'am, I have not compared it with that direct conversion one, ma'am. Like this sensitivity is more increased. I mean, increased in the case of indirect conversion, ma'am.
The sensitivity in the sense attenuation.
Yes, ma'am.
Okay, okay. Have you determined the crystalline structure of your the material?
Yes, ma'am. Tetragonal phase, ma'am.
Okay. You confirmed.
Yes, ma'am. I have confirmed it with the XRD patterns, ma'am.
Okay, good.
Yes, ma'am. Thank you, ma'am.
Yes, ma'am. Yes, ma'am. Good afternoon, ma'am. Yes, ma'am. Is my screen visible now? My topic is about evaluation of solubilization of curcumin with the biocompatible polymers. Photodynamic therapy uses a drug that is activated by light, which is also known as photosensitizer or photosensitizing agent to kill cancer cells. The photosensitizer we have chosen here is curcumin. It is an active ingredient of curcul longa plant, which has gained attention over the past 2 decades for anti-cancer and anti-inflammatory agents. There are several factors for targeting specific cancer cells without even causing side effects can be seen here. Various drug delivery systems have been formulated using different nanotechnologies that will improve curcumin property and targetability. So, biocompatible and biodegradable polymers such as polyvinyl pyrrolidone is added to the photosensitizer. In addition to this, to increase the permeability of curcumin and PVP system, polyethylene glycol is added as a penetration enhancer. It has been found that it enhances the solubility of curcumin in the polyvinyl pyrrolidone polymeric environment. The interaction between curcumin and PVP can be seen here. It shows a gradual increase in the fluorescence intensity of curcumin with increasing composition of PVP along with minimal blue shift in the emission wavelength. So the solubilization of curcumin with polyvinyl pyrrolidone is observed from the increase in fluorescence intensity. In the neutral form, curcumin is found to undergo tautomerism and available as an enol, which increases the rigidity of molecule. Fluorescence intensity of curcumin increases slightly with small shift in emission wavelength with the addition of polyethylene glycol. Formation of ternary system of curcumin, PVP, and PEG can be seen here. A possible association of curcumin is suggested by mode of interaction. That is, curcumin is incorporated into hydrophobic of polyvinyl pyrrolidone polymer, which in turn associates with polyethylene glycol. Further, to analyze the mode of association, fluorescence anisotropy measurement of this ternary system will be carried out in the future. The interaction between the system is slightly disturbed, so this leads that curcumin exhibit a better environment. Hence, it can be seen that among the various solubilizer tried for curcumin, a biocompatible polymer were found to be more advantageous when compared to others. And to increase this permeability of curcumin and polyvinyl pyrrolidone, polyethylene glycol is added as penetration enhancer. That's it.
Okay, more, yeah. Okay, can you elaborate on the significance of your study?
Ma'am, through this we can know that it can be used in pharmaceutical areas, ma'am, to cure cancer cells. That is, through this therapy, it destroys only the cancer cells, but not the other active cells. It is widely used in pharmaceutical agents.
Okay, thank you.
Thank you.
Yeah. Okay.
Is it visible, ma'am? Okay. So my presentation is about organic dye immobilized carbon nanomaterial modified electrode for electrochemical sensing. The organic dye used here is methyl violet, or also called as crystal violet, which has a very good antibacterial and antifungal properties. Here I also reported about the sulfide sensing using sodium sulfide. Sodium sulfide is also considered as a major area of research because it is also applied in various fields. In my first study, methyl violet immobilized carbon nanomaterials like carbon nanotubes, graphite nanoparticles, activated carbon, graphene oxide, modified glassy carbon electrodes were subjected in pH 7 phosphate buffer solution. The graph obtained in cyclic voltammetry showed that the methyl violet immobilized carbon nanotube modified electrode showed the efficient peak, which is shown in the figure 1. In the next study, methyl violet immobilized carbon nanomaterials are subjected in 500 micromolar of sodium sulfide, in which the methyl violet immobilized carbon nanotube modified electrode showed a well-defined peak in the CV graph, which is also shown in the figure 2. So I took methyl violet immobilized carbon nanotubes modified electrode for the further studies. The effect of concentration of sodium sulfide on methyl violet immobilized carbon nanotube electrode was studied. This showed a linear increase in the oxidation peak from 100 micromolar to 6.5 millimolar. And by the amperometric method, the sensitivity was found to be 1.25 milliampere, which is also shown in the figure 3. The next study is about the effect of scan rate of sodium sulfide on methyl violet immobilized carbon nanotube modified electrode. It showed an absorption controlled reaction, which is showed in the figure 4. And my future work will be on the effect of pH of sodium sulfide on methyl violet immobilized carbon nanotube modified electrode. The interference effect should also be done to check whether any other particles interfered. After that, the real sample analysis should be done to identify the presence of sodium sulfide in the water, etc. And go for characterization to get a clear results. Then the next study is on introducing some suitable enzymes to check whether they have any impact in the sensing efficiency of sodium sulfide. And my conclusion, by all the studies on the effect of concentration scan rate, it is clearly known that the sensing efficiency of sodium sulfide increases by increasing the scan rate and concentration. Thank you.
How did you choose methyl violet? How many such how did you do the literature survey to conclude on methyl violet?
Methyl violet is a dye, so it will absorb in the nanoparticles effectively.
No, correct. How many such dyes are available? No.
Yes, ma'am.
How did you come to a conclusion to take methyl violet for your study?
By literature survey, ma'am. I have seen.
Okay. No work has been done in methyl violet so far? Such type of work?
It has been done, ma'am, but with carbon nanotubes, it is new, ma'am.
Okay, thank you.
Okay, ma'am. Thank you.
Yes, ma'am. Yes, ma'am. Ma'am, is my screen visible, ma'am?
Yes, proceed.
My presentation is about understanding the association of surfactant to form mixed micellar by fluorescence probing approach. So most of the surfactant substances are employed in daily applications like in soaps, shampoos, detergents, etc. Here, the surfactant will act as a drug delivery system in formulating the ANS, that is 8-anilino-naphthalene sulfonic acid, that is ANS, as a fluorescent probe. Probes are like ANS or methylene blue, whose fluorescent spectra were responsive to the polarity. This study establishes that fluorescence property can be used in probing the micellization behavior of sodium chloride and sodium dodecyl sulfate. The molecule ANS is hydrophobic. So since it is hydrophobic, the solubilization of ANS possesses a disadvantage. So in order to increase the solubility and enhance the bioavailability, it is suitable to use
tell what work you have, Aishwarya, tell what work you have done, what the result and the conclusion.
Yes, ma'am. So here the association of surfactant and bile salt is done. The surfactant I have chosen is STS, sodium dodecyl sulfate. It have a long hydrophobic tail and a polar head. So aggregation of surfactant molecule was obtained through a fluorescence probing approach. First, stable STS core was formed, and thereafter, due to the entering of sodium chloride molecules, what happens is the size of the micelle is increased. So the result is association of ANS, SDS, and sodium chloride was evaluated by PL spectra. PL spectra is recorded by measuring the intensity of emitted radiation as a function of excitation wavelength and emission wavelength. So excitation spectrum is obtained by monitoring emission at a fixed wavelength. Similarly, emission spectrum is obtained by monitoring the excitation at a fixed wavelength. So I conclude that mixed system of STS and sodium chloride are used to study the formation of mixed micellar system. The micelles consisting of STS and sodium chloride mixture was used for drug delivery and as a anesthesia or antibiotics, etc. That's it, ma'am.
Okay. Any other application of your study? Or significance, or in what way your study is different from the one that is already existing?
They have done with probe methylene blue, ma'am, and I'm doing it with ANS.
No study has been done on ANS with surfactant?
No, ma'am. No, ma'am.
Okay, thank you.
Thank you.
Ma'am, Bharat, I will explanation, ma'am. Bharat அவங்க explanation பண்ணுவாங்க, ma'am.
Hello? Yeah, ma'am. Yeah, one second. Good afternoon to one and all. Myself, Bharat Kumar from MGR University, and okay, one second, ma'am. Is that visible now, ma'am? Hello?
Yes.
Yeah. Okay. Good afternoon, one and all. Myself, Bharat from MGR University. We are doing a project under ultrasonic investigation of interaction of cleaning agents with humans, generally with dishwashing soaps, bars, and other chemicals under the guidance of Dr. N.S. Subhashri. For this, we took three different types of sample. One is a dishwashing gel and a soap bar, and alkaline benzene sulfonic acid, which is commonly known as Sabina. We used these three samples, and we created 6 different samples with dissolving these with distilled water, and you can see the fundamental parameters like ultrasonic velocities, densities, and viscosities under this table. We used the ultrasonic interferometer to calculate these values, and as you can see that the value of the last sample, which is sample 6, is higher. That one is alkaline benzene sulfonic acid, Sabina. So we use this particular sample to UV test to calculate the wavelength. As the result of the UV test, we concluded that this particular sample has higher wavelength of approximately 223 nanometers. This is a project based on, and as per the conclusion, we conclude that Sabina is less harmful to the human skin, and it is an insulating properties compared to other soaps and was available in the commercial market. Hello? Yeah, that's all, ma'am.
Okay, Bharat.
Yes, ma'am.
Bharat.
Yeah, ma'am.
Yeah, please give the significance and applications of your study.
Significance. Yeah, ma'am. Actually, we compared with soaps, that is dishwashing soap and bar. So comparing the Sabina with other two products, it is.
I think Tilaga, please mute your mic. I cannot hear.
Comparing the Sabina powder with the soaps and dishwashing gel available in the commercial market, it is known to have less chemical interaction with human body skin, ma'am, and it is also an insulating property, so it also has less thermal conductivity and electrical conductivity. The other two samples are as some harmfulness to the human skin. That is our project based on, ma'am.
Okay, thank you.
Thank you.
Ma'am, shall I share my screen, ma'am? Okay. Is it visible, ma'am? Okay, ma'am. I am here to present my work on crystal growth and characterization of cesium sulfate to 4-methoxyaniline. This is a single crystal for NLO and antimicrobial applications. And as we all know, organic crystals have been found to exhibit potential application in NLO, nonlinear optics, with an intention of identifying new material. An attempt has been made by us to modify 4-methoxyaniline by adding cesium sulfate. And in this work, slow evaporation method has been adopted to ground the crystal. In 10 gram of 4-methoxyaniline salt was dissolved in ethanol and water mixture, and 1 gram of cesium sulfate was added. Then it was stirred for 3 hours and allowed to crystallize. And optically good quality crystals were collected after a period of 25 days. And coming to result and discussion part, the XRD analysis reveals that the grown sample crystallizes in orthorhombic crystal structure with centrosymmetric space proof. And the IDAC spectrum reveals that the experimental percentage of elements found in the grown crystal. The nearby image, the same image reveals that the emergence of interlaced structure by slip lines. And upon the face of crystals grown by slow evaporation method, that is solution technique, such interlacing patterns are usually found. And coming to UV analysis, the UV analysis suggests that from 296 to 1100 nanometer, the grown crystals have outstanding transparency, and the cutoff wavelength was observed to be 231 nanometer. Also, the band gap was determined to be 5.04 electron volt. And coming to mechanical analysis, the first plot shows that the hardness number rises as the applied load increases. And from the graph of log P versus log D, the value of work hardening coefficient is determined to be 3.469. And this reveals that the grown crystal falls into the category of soft material. And coming to the magnetic studies, the graph shows the diamagnetic nature of the grown sample. Coming to the impedance analysis, the plot shown here depicts the frequency-dependent real and imaginary parts of grown crystal.
and the values of real part seems to converge at higher frequencies, and this is due to the reduction of space charge. And then coming to the next plot, that is the Nyquist plot or Kohl-Kroll plot. The semicircular arcs gives the boundary,
conclude, please.
grain boundary resistance, also the bulk electrical
Conclude,
resistance.
please.
And coming to SHE analysis, the SHE analysis is 1.67 times with respect to that of the KDP crystal, and which shows good SHE applications.
Conclude your.
And coming to the Z-scan application, the scan was used to always explore third order NLO properties, and the OA and CA curves are depicted in this figure. The high susceptibility value, which is shown in the table that has been calculated from the plot, shows potential application in optoelectronics.
Yes, ma'am, please conclude.
And next, coming to antimicrobial activity, the zone inhibition for the various bacteria and fungals is shown in the table.
Tilaga, please.
And according to the finding, the bronze crystal exhibits superior antibacterial and antifungal activity against the tested pathogens. And coming to the conclusion, the single crystal XRD diverges. Single crystal XRD diverges the gold crystal belongs to orthorhombic crystal system, and the microharness analysis, microstructure of CS MOA, that is cesium sulfate group 4
Tilaga, please conclude.
And the linear optical analysis shows high transmittance. Also, the optical variables such as energy band gap are calculated. And coming to mechanical investigation, that reveals that the material belongs to a soft category, and the diamagnetic nature was corroborated from VSM analysis, and the electrical properties was also investigated by impedance analysis. And the SHE analysis shows that the efficiency was 1.32 times that of the conventional KDP crystal.
Madam,
and the Z-scan analysis shows high third order NLO susceptibility. And with all this result, it's concluded that the drone sample has potential nonlinear applications, and also it shows good antimicrobial effects against the tested pathogens. Thank you, ma'am.
You just went in a flow. I'm just asking you to do the conclusion. You didn't even listen to what is happening. What is the significance of your work? Okay, madam, move on to the next one, please.
Yes, ma'am.
Madam, excuse me. Is the name in the list? No, just.
Ma'am, if my screen is visible to you, ma'am.
No, just tell the presenter name, Sarumati. Yeah.
Okay. Shall I start, ma'am?
Yes, ma'am.
Very good afternoon to all. I'm Sarumati. I'm doing my BSc Physics final year at the Krishnaswamy College of Science, Arts and Management for Women, Kadalur. I'm so thankful to Dr. Bhuvaneshwari ma'am to guide me to all of this project. Now I'm start with my topic, the ionic conductivity of a biopolymer, polyvinyl alcohol with Indian medicinal plant, Acalipa indica and potato extract for electrochemical device and applications. The aim of the project is to prepare and characterization of a PVA-based polymer electrolyte with Indian medicinal plant, Acalipa indica and potato extract. The introduction is the polymers plays a vital role in technological applications such as drug delivery, fuel cells, sensors, and etc. Acalipa indica is one of the important medicinal plant for human health applications. Potato is a starchy plant, a tuber, and important food crops, and also have a potential to electric charge. The experimental technique we used is a solution casting method.
The polymer we used is an polyvinyl alcohol PVA. The solvent we used is an Acalippo indica and potato extract. We do characterization under XRD, FTIR, and impedance analysis. Now the XRD results are shown in figure. XRD pattern shows an increase in the amorphous nature of the polymer electrolyte due to the addition of arginine. The amorphous has been observed for the composition of 1 gram of PVA to 50 ml of Acalippo indica and potato extract. The XRD studies confirm that the complexation has occurred in the polymer matrices and the complex found is amorphous. FTIR results shown in figure. The FTIR results confirm the complex formation between PVA and Acalippo indica and potato extract. FTIR spectral assignments of a PVA with arginine polymer membranes are tabulated. The observed peaks, shift, and the variation in intensity of a FTIR spectrum suggest that the complete complexation of a PVA with arginine. Now move on to AC impedance spectroscopy. The complex impedance plot for a different composition of a pure PVA and Acalippo indica and potato extract at 303 Kelvin are shown. At high frequency, it forms a semicircle due to bulk capacitance CB and bulk resistance of the sample. At low frequency, it forms a spike. The bulk resistance can be calculated from the intercept of a high frequency semicircles or a low frequency spike on the x-axis. The ionic conductivity values of a PVA, Acalippo indica, and potato extract polymer electrolytes from the impedance plot at room temperature. At 303 Kelvin, pure PVA has a conductivity of 2.14 into 10 power minus 9, and when it adds with an Acalippo indica, the conductivity is increases to 1.5 into 10 power minus 4.
Please move on to conclusion.
Okay, ma'am. As conclusion, the PVA-based polymer electrolytes with Acalippo indica and potato extract has been prepared by solution casting method. The XRD analysis reveals the increase in amorphous nature of the polymer electrolytes. FTIR provides evidence for the existence of an interaction between PVA and the Acalippo indica and potato extract, thereby revealing the complexation in the prepared polymer electrolytes. From the conductivity analysis, the higher conductivity at room temperature has been found to be 1.5 into 10 power minus 4 with the PVA and Acalippo indica electrolyte. Thank you, ma'am.
What is the application of your study?
We can use this for electrochemical cells, ma'am.
Electrochemical?
Electrochemical devices.
How? What is the existing electrochemical device? What is the one that is used now? And how your work is significantly good when compared to the existing one?
Sorry, ma'am, I don't know, ma'am.
You don't know?
Yes, ma'am.
Okay, thank you.
Thank you, ma'am.
Good afternoon, ma'am. I'm Rogini. I got interrupted in the middle due to internet connection. Sorry, ma'am. Can I present now, ma'am? Yes, ma'am.
Yeah, okay.
Is my poster visible, ma'am? Yes, ma'am. Okay. I'm Rogini from Methodology College for Women Chemistry Department. My poster is based on synthesis and characterization of zinc oxide nanoparticle with novel polymer. In general, zinc oxide is a semiconductor quantum. Zinc oxide is a semiconductor nanoparticle, which have the band gap energy of 3.37 electron volt. And zinc oxide have wide application in fluorescence and it have high mechanical and chemical stability. And the synthesis is carried out with the leaf extract of Eclipta alba, which is treated with zinc oxide trihydrate as a precursor. The zinc oxide nanoparticle synthesized is carried out at the room temperature under normal conditions. The stirring is carried out for 1 hour with the addition of CTAB. CTAB is cetyl trimethyl ammonium bromide, which is a 16 carbon long chain. So, which is used to maintain the size and morphology of the compound. The polymer, the zinc oxide nanoparticles.
Brief on your work. What result and conclusion?
Yes, ma'am. So I treated the zinc oxide nanoparticle with a polymer and it formed a thin film. I studied the photocatalytic activity of the zinc oxide nanoparticle. The size effect of the zinc oxide nanoparticle was obtained as 76 to 85 nanometers range, and the polymer incorporated zinc oxide nanoparticle were also found to observe dye degradation. The dye degradation is carried out with methylene blue dye. The methylene blue dye in general shows 663 nanometer in UV visible spectrum, but on the incorporation of zinc oxide, the dye degradation is decreased and the pi to pi shift and absorption of nanoparticle decreases, which indicates its photocatalytic activity. And I conclude that the compound zinc oxide nanoparticle act as a photocatalyst, which provides both oxidation and reduction environment simultaneously. So we can use to remove heavy metal elements. The C-tab here I used is also used to remove heavy metal ions from waste like silver, lead. It have a efficiency up to 85%, and I placed the two images which indicates the size of the zinc oxide nanoparticle and the polymer incorporated zinc oxide nanocomposite. The polymer incorporated zinc oxide nanoparticle is it's in flower shape, and the normal zinc oxide. Yes, ma'am. Finally, I conclude that it acts as a photocatalyst and the binding set of the polymer quenches the fluorescence, but the substrate binding inhibits the fluorescence quenching and enhances the fluorescence.
What is the sample? What is the material, ma? Okay.
Sorry, ma'am.
What is the material you are using?
Zinc oxide, ma'am.
Okay.
Zinc acetate dihydrate as precursor.
So your study is on photocatalyst.
Photocatalysis and photocatalytic dye degradation.
Okay. How far your work is innovative and compared to the traditional one already available?
I innovated it with the polymer, and it is actually traditional one because there is a green synthesis, and I innovated with the polymer, and I am working on computational model as well, ma'am, right now.
What model?
Computational model.
Okay. Okay. Thank you. Madam, I just read out those who have not done. Atulya. Those who have not done today, I'm reading the names. Atulya has not done. Sivaranjani Babu. Satish. I think that Harini did with Atulya, I think. Yeah. And that Sivaranjani Babu, Satish Kumar Paramasivan. Yeah, Rakshita. Then Aravindan, Mohammed Rafi, Gopinath, and Muttu Ganesh Manta. Oh. Okay. So shall we conclude it? Yeah. Yeah. Okay. Yeah. Yeah. Okay. Thank you. Thank you for the opportunity given. Thank you.
Hello. Um, am I audible? Okay, fine. Okay. Okay, now I will then switch on the video.
Good evening, sir.
Good evening.
We welcome you, sir. Yeah, we are beginning the valedictory section.
Okay, fine. Start.
Okay. Very good evening to one and all joined. We welcome you all to the valedictory session. Today, we have amongst us Dr. S.V. Kashmir Raja, convener of ISCA, Chennai chapter, Director of Research and Adjunct Professor in the Department of Computer Science, SRM University. A warm welcome to you, sir. Now I request Dr. B. Uma, Assistant Professor, to introduce the chief guest to the participants. Thank you, ma'am.
Yes.
Now I request Dr. S.C. Kashmiri Raja, sir, to take over.
Okay. Respected Chairman of Ethiraj College Trust, respected Principal and Secretary of Ethiraj College of Women, the Head of the Department of Physics, the organizers of this two-day function, two-day conference, faculty members, students, and participants from other institutions. I feel proud to join this two-day international conference on condensed matter physics and materials. Nowadays, the matter are materials. Everybody is interested in materials. All the branches, even if you take chemical engineering, they study the materials, chemistry department, physics department, even mechanical engineering, communication engineering. They are all do research on materials because that is the future of our world, because it has lot of applications. And the Department of Physics of Ethiraj College has arranged this international conference to enlighten the students and the researchers on the properties of condensed matter physics and the materials. Now, it is a current topic, so the students and researchers should know, and lot of research is going on in these areas. The condensed matter physics includes the condensed phases of matter and its physical properties. This also includes the laws of quantum mechanics, statistical mechanics, electromagnetism, etc. This field is closely connected with material sciences, chemistry, nanotechnology, biophysics, and atomic physics. Theoretical condensed matter physics shares many significant techniques and concepts with nuclear physics and theoretical particles also. And now, to do research and continue in this area of condensed matter physics, is there any courses available for the students? Yes, the condensed matter physics offers courses at both UG and PG levels. Your students almost all are studying in BSc physics, and the masters of condensed matter physics is applicable to these students, and if they have a net, then they have a bright future for them. Now, some of the best places where you can pursue your PG masters in condensed matter physics, there are plenty. For example, you can say Indian Institute of Technologies, Indian Institute of Geomagnetism, Jawaharlal Nehru University, IIC Bangalore, Saha Institute of Nuclear Physics, Indian Institute of Physics, Anna University, etc. Okay, after completing your PG, what I should do? If you have net, you can join as a lecturer in the colleges, and if you have scored good marks in your PG, you can join in research and take up jobs in some of the institutions in India. For example, ISRO, DRDO, Intel, AMD, Skyworks Solutions, Virginia, Baba Atomic Research Center, etc. And in these centers, in these research institutions, you can find a job. Or the best thing would be to take up research. Now, what are the sciences and engineering are 4 areas. The areas are energy production and storage, electronics and photonics, bio-inspired materials and systems, and green technologies. In the last 2 days, that is yesterday and today, we have listened to many resource persons. They have covered almost all the areas in the material sciences. And even today, you had a chance to listen to 4 eminent people, and most of them have concentrated on energy, because alternate energy is required, because the conventional energy produces carbon dioxide. That is the cause for our climate change and all the other things. So alternate energy production and storage is a current problem in the world. Anywhere you go, this is the problem. So energy research will prove to be the most prosperous growth area. The department, colleges, and universities. The inevitability of an energy crisis and global climate change has intensified efforts in alternative energy research around the world. Among the many possible sources of alternative energy, the following are particularly aligned with current materials. They are photocatalysis, photovoltaics, thermoelectrics, phononics, batteries, and supercapacitors. So this is a fine area, and also here nowadays they concentrate on hydrogen fuels. Using hydrogen fuel, they try to run motors. For example, the ICF is taking up a project to run their locomotive with hydrogen fuels. And for that, SRM Institute of Science and Technology students help them. They give the concepts for the production of hydrogen, and then mixing the hydrogen with oxygen, how the electricity can be produced, and how they can be stored in batteries, and how they can be used to run the electric locomotive of Indian Railways. And another important area is electronics and photonics. Electronics and photonics are considered premier growth areas. New materials. See, even I happen to listen to some of the poster presentations. In most of them, have taken new materials, synthesized them, and analyzed. And what are the areas, what are the applications of these materials, like that. So new materials and processing techniques are needed. Advances in nanoscale fabrication have led to recent advances in the following areas: oxide semiconductors, 3D integration, materials beyond silicon, high K and low K dielectrics, plasmonics, spintronics, and multiferrics. And third one is bio-inspired materials and systems. So most of the researchers get inspiration from the nature, from the plants, from the animals. So scientists and engineers are increasingly turning to nature for inspiration. The solutions arrived at by natural section are often a good starting point in the search for answers to scientific and technical problems. So from the natural inspiration, we'll be able to get some solution to our problems. The following areas are particularly aligned with the current materials research. They are bio-inspired composites, engineered protein films for adhesion, lubrication, and sensing applications, so well as biomaterials for tissue engineering and drug delivery. And the fourth important area is the green technology. Now, carbon dioxide is doing all the havoc in the world. They are produced largely from AC plants, refrigeration, etc. So the CO2 has to be contained, or they have to be used for something else, some useful one. So a lot of research is going on in green technologies. The 21st century has been called the century of environment. Neither governments nor individual citizens can any longer assume that social challenges such as pollution, dwindling of natural resources, and climate change can be set aside for future generations. Strategies for clean and sustainable communities need to be established now. A drawing era of creativity and innovation in green technology is bringing the promise of a healthier planet. Healthier planet means our world. The researchers have targeted green composites and new systems for CO2 capture and conversion in areas for future growth. So there's pollution. Last month we had a rally organized by Indian Science Congress Association for eradicating the use of one-time use plastics. And this one-time used plastics are just thrown away on the earth. So they make a cover on the earth. So water will not get into, the plants will not grow like that. So this is one of the pollutions. And major things are the CO2. And all the governments, especially the UNO, they are speaking and formulating so many things, but nothing has happened. People are not aware of the dangers of such kind of pollutions. And normally every year UNO used to arrange a conference on climatic disturbances, climatic changes. And in one of the conferences, just 2 years back, one teen environmental activist, Greta Thunberg, you would have heard about that. She is from Sweden, just 17 years old, delivered an emotional and scathing speech at the United Nations, accusing world leaders. She says that you are talking. Nothing has happened. So she says, you have stolen my dreams and my childhood with your empty words. People are suffering. People are dying. Entire ecosystems are collapsing. What are you doing? We are in the beginning of the mass extinction. And all you can talk about is money, fairy tales of eternal economic growth. You don't bother about the world. You don't bother about the pollution or climate change. Entire ecosystems are collapsing. We are in the beginning of mass extinction, and all you can talk about is money. So this is the angry speech given by that teenage girl. And our Indian government also doing a lot of things, but it doesn't reach the people. And see this green energy. Now, one of my students, he did a PhD in this energy or the refrigeration. So when a refrigerator runs, it produces carbon dioxide. So that carbon dioxide should be removed. So he did a research on the magnetocaloric property of novel magnetic oxide, mainly iron oxide materials, for environmental friendly refrigeration. So he selected a few oxides, magnetic oxides, and he magnetized them. And after magnetization is over, he demagnetized. And you'll get a hysteresis graph. So when demagnetization happens, the temperature lowers. Thereby, it goes below 20 or 15 degrees centigrade. So the refrigerator functions with this without producing carbon dioxide. So like that, research on materials are required We have to do research on such things so that we can save the world, we can save the earth. Now, for this, the Department of Physics has taken a great effort in organizing such a conference. And now I have to say a few things about Indian Science Congress Association. It is a premier scientific organization of India with headquarters at Calcutta, coming under the Department of Science and Technology, Government of India. So Science and Technology, Department of Science and Technology supports this Indian Science Congress Association. It was started in the year 1914 at Calcutta. Now it meets annually in the first week of January from 3rd to 7th, and they discuss so many things. And it has a membership of more than 30,000 scientists. The main objectives of the association are to advance and promote cause of science in India, to hold an annual congress at a suitable place in India, to publish proceedings, journals, transactions, and other publications. And the main objective of Indian Science Congress Association is to inculcate the scientific temper among the people, among the villages, among the students, and encourage young scientists to grow up steadily in this direction, involving them in the programs relevant to fundamental, experimental, and operational activities. To achieve these objectives, there are 26 chapters all over India, and the Chennai chapter is one among them, and I am the convener for that. What do? We take science to the rural areas, to the colleges, to the villages, and we conduct conferences, workshops, symposia, awareness programs, and this is being co-sponsored or supported by schools, colleges, and villages. And I'll cite one example. Now we are organizing a 5-day workshop for the tribal people. The tribal people in Yelagiri Hills, which is near Vellore. There are a number of tribal villages, and they do not know how to cultivate, how to sell the products, and so on. So we are planning to have a training program for them, how to cultivate and improve the production, and how to sell the products. So for this, we are going to give training. That is, Indian Science Congress Association, Chennai chapter is organizing this in Yelagiri Hills. And every year, this is important, the Indian Science Congress are being held in some important city in India from 3rd to 7th January. Every year, a focal theme of national relevance is chosen, which is discussed in every section, every committee, and in every forum during the annual session. It is customary that it is inaugurated by the Honorable Prime Minister of our country. This year, it was held in Nagpur from 3rd to 7th January 2023. I attended that conference. More than 20,000 delegates, mostly students from all over India, participated in that. And this year theme of the Congress was Science and Technology for Sustainable Development with the Empowerment of Women. This year we had a special program for women personalities who achieved something with hard work and removing all the hurdles they have come up, and such program was there in the Congress. These apart, several plenary sessions are organized around the various facets of the focal theme, in which scientists and technologists as well as policymakers and administrators interact with one another. So some policies will be made, scientific policies will be made, and these policies will be sent to the government for their action. And there will be Nobel laureate lectures also. Those who have got Nobel prizes, they are invited. They will give talks, and they can freely interact with the students. And there will be invited talks, guest lectures, etc. And another important thing is, every evening from 3rd to 7th, there will be a cultural program arranged in the evenings. And I cite one example. When a science congress was held in Mumbai, the famous actress Hema Malini gave a 2 hours program, dance program on Kannan and Radha. It was a wonderful dance program. She danced for almost 2 hours. You know, her age is around 80. So, such a cultural programs are very, very useful for us. And there are 14 sections depending on their area of research or depending on the subjects. And one of the section is physics. In the physics section, every day in the evening, they will have invited talks. They will have paper presentation, poster presentation, and the papers will be adjudged, and finally, the good paper presentation, oral presentation, as well as poster presentations will be given awards. And another thing is, there is a communicator, science communicators meet. It is organized there, and each chapter, say for example, Chennai chapter can select 4 science communicators and send them to the Congress. These communicators, they will present. See, science communicators means they have to impart their science aspects, concepts to the public. So such meeting will be there, and chapters will select the communicators, and they will be sent to the Congress, and they will be given 3rd AC train fare, accommodation, and other hospitalities like food and stay, etc. So if you do well, there is a chance that you can also be selected for the science communicators meet. ISCA is a professional body, and nowadays government says that the students as well as the faculty members should be a member in a professional body. And one of the criteria in NAC assessment is that the management of a college or any institution should come forward to make their faculty members as the life members of Indian Science Congress Association. They're asking for how much you are spending for this. How many faculty members have become the life members. And for that, they want the evidences also. So if you become a member, a life member in the Indian Science Congress Association, it will be helpful to you as well as it will be helpful to the institutions also. In the NAC accreditation, you will get good marks. And not only that, as an individual life member, there are many awards. You can apply, you can give your biodata, and you can also compete with others for the award of certain awards. For example, Abdul Kalam Award, like that. There are a number of awards there. You can also win the coveted titles. And not only that, you will be receiving Everyman Science Journal every month. And you also have a voting right to elect the executive members and council members of the Indian Science Congress Association. So if you join, you will be benefited and your institution will also be benefited. So with this, I will complete this Indian Science Congress Association. And now come back to this conference. I really congratulate the head of the department and other professors, including Dr. Mahalakshmi. And they have done a wonderful job, and they have taken the concepts on matter physics, condensed matter physics, and materials to the students, and thereby it will go to the public. So I congratulate the department once again, and I will congratulate the management for supporting this. And as a convener, I am very much pleased to involve ourselves, collaborate ourselves with the physics department of the well-known Etiraj College for Women. So with this, I thank you, congratulate you once again, and with this, with all our wishes, I will close this valedictory address. Thank you very much. Hello?
Thank you, sir. Thank you for enlightening us with the topic on energy harvesting.
Yeah.
I am Aparna. I will present the report of the conference. I am very delighted and proud to present the report of two-day international conference on condensed matter physics and materials ICCMPM 2023. The Department of Physics is engaged with various research activities in various fields of science and has been consistently organizing national and international conferences, workshops, seminars, and lecture series celebrating National Science Day to inculcate research flame amongst the younger minds. Two-day international conference on condensed matter physics and materials ICCMPM was successfully organized by the Department of Physics in association with the Indian Science Congress Association, Chennai chapter on 28th February and 1st March 2023 in a hybrid mode. The conference owes its success to the able guidance of Dr. A.V. Joni Virgula, Head Department of Physics, and the hard work put in by the entire team comprising Dr. S. Abhirami, Head Department of Physics Self-Supporting, Dr. J. Bhavani, Dr. G. Rajeshwari, Dr. B. Uma, Dr. S. Mahalakshmi, Dr. M. Amuda, Dr. E. Porselvi, Dr. D. Dugalakshmi, Dr. N. Kavita, Dr. S. Leela, and Dr. N. Aparna Devi, research scholars and student volunteers. The presence of dignitaries, an impressive lineup of academicians from across the state, the support of Indian Science Congress Association Chennai chapter, an array of carefully selected, well-researched and well-presented papers on the subject all came together to help conference team ICCMPM 2023 to admirably conclude this huge endeavor. Heads and faculties from different departments of the college graced the event. The conference was uploaded by research scholars for the 3 plenary sessions on day 1 and 4 plenary sessions on day 2 by the resource persons, oral and poster sessions for the paper presenters on both days, besides the inaugural and valedictory sessions. With the blessings of Almighty, and our revered founder, Thiru V.L. Ethiraj, inaugural session began by greeting Tamil Thai. Dr. A.V. Joni Virgula, convener ICCMPM-2023, welcomed the August gathering with her warm words. Dr. S. Abhirami, co-convener of the conference, presented the theme of the conference in a lucid manner for the understanding of the audience. Our chairman, Thiru V. M. Muralidharan, expressed his felicitations and motivated the students on how important it is the science and research in our day-to-day life. Dr. D.B. Usharani, principal in charge, felicitated the department for the effort taken to organize the conference and conveyed her best wishes. She also suggested to conduct, once again. Dr. D.B. Usharani, principal in charge, felicitated the department for the effort taken to organize the conference and conveyed her best wishes. She also suggested to conduct multidisciplinary conferences in the future. The chief guest and other dignitaries were honored with a memento as a token of love and gratitude from the department. The research abstract contributed by the academic committee were released as the book of abstract during the inaugural. The chief guests of the day, Padma Bhushan and Padma Shri Dr. A. Sivatano Pillai, released the book, and the first copy was received by our chairman. The Honorable Chief Guest, Padma Bhushan and Padma Shri Dr. A. Sivatano Pillai, distinguished scientist, board member, Ethiraj College Trust, former Chief Controller, Research and Development, DRDO, former CEO and MD of BrahMos Aerospace, inaugurated the conference by addressing the gathering on the future scope of materials research in various fields such as agriculture, medicine, and defense. The lead keynote speaker of the day, Dr. R. Venkatesan, former head, Radiological Environmental Safety Department, IGCAR, Kalpakkam, Tamil Nadu, sailed the gathering into the conference theme by his enlightening keynote address. He motivated the students to elevate their practical knowledge. On behalf of the department, Dr. B. Uma acknowledged the encouragement and the support rendered by our chairman, Thiru V. M. Muralidharan, Ethiraj College Trust, Dr. D.B. Usharani, Principal and Secretary in charge, and Dr. T. Usha Priya, Vice Principal Self-Supporting, and the efforts of the whole conference team. Inaugural session was concluded with the college song. The conference was highly applauded for bringing together great minds from different fields. All the resource persons conducted very engaging and fruitful sessions. Day one session started with a talk by the speaker, Dr. S.P. Vanitha Kumari, scientist, IGCAR Kalpakkam. She delivered elegant talk on biomimicry, nature-inspired surface modification of materials. A lucid presentation was delivered by Professor C. Rakappan, Head Department of Physics, Annamalai University, Chidambaram. He delivered his thought on research and its importance and focused on quotient structures of nanoparticles for efficient enhancement of properties. The afternoon session began with an online talk by Dr. Jason Savio, scientist, Defense Metallurgical Research Laboratory, DRDO, Hyderabad. He elaborated on the ceramic materials and its armor applications. Day 2 began with online session on materials physics for energy applications by Professor Ramurthy Ramesh, Vice President, Research Professor, Material Science and Nano Engineering, Rice University, USA. He gave an insight on the cost-effective and efficient materials used in energy harvesting. Professor Dr. Aish Abdul Jalalil, Center of Hydrogen Energy, Institute of Future Energy, Department of Chemical and Energy Engineering, University Technology, Malaysia, gave an insight on fibrous silica-based catalyst for methane dry reforming. The third session of the day was taken over by Dr. D. Paul Joseph, Associate Professor, Department of Physics, National Institute of Technology, Warangal. He elaborated on the nano-dimensional thin films for optoelectronic and energy harvesting devices. Dr. Sindhuja Manoharan, Faculty of Applied Energy Systems, Jeju National University, South Korea, elaborated on the electrochemical energy devices. The views, discussions, and active questioning and participative action in these sessions made the audience see how materials are researched from different aspects, how they are implemented for practical uses, and what are the future challenges awaiting. There was also an emphasis from the speakers to take up internships and projects during graduation to explore the world of research. Moving on to paper presentations in oral and poster sessions, more than 210 participants from various institutions across India and abroad have registered for the conference to participate and present their papers. On day one, oral session was conducted with 11 presenters at the Ethiraj College auditorium, and 5 participants presented online through Gmeet. On day 2, 18 participants presented their papers in oral session and 22 participants in poster session through online mode. Results of oral and poster sessions were judged by expertise, and the results will be announced shortly. The conference has shown the way as to what can be achieved being supported by the institution and the Indian Science Congress Association, Chennai chapter, and the active participations from students and academics. This conference has, without a shade of doubt, made the academic fraternity richer, incisive, and insightful discussions. This two-day event offered opportunities to the participating audiences to interact with the academicians, scholars, and experts over the globe who deliberated upon and covered topics in condensed matter and materials physics. The views expressed and explored on this platform by the resource persons and paper presenters would have definitely made the audience rethink ideas which we cling on unthinkingly in our day-to-day life. With this note, I thank everyone and the conference team for giving me an opportunity. Thank you. Now I request Dr. B. Uma, Assistant Professor, Department of Physics, to announce the results of oral and poster sessions. Thank you, ma'am. Congratulations to the winners. Now I request Dr. S. Mahalakshmi, Assistant Professor, Department of Physics, to deliver the oath of thanks.
Thank you, Aparna. So good evening to the dignitaries present online and offline, and to my dear students. It's my privilege and pleasure to propose vote of thanks in the two-day international conference on condensed matter physics and materials in association with Indian Science Congress Chennai chapter. First, I would like to thank the great Almighty for making this international conference a great grand success. I would like to thank our respected chairman, Thiru V.M. Muralidharan, and trust board members for their unstinted support for this event. I would like to thank our beloved principal, Madam, and Secretary in charge, Dr. D.B. Usharani, and Dr. T. Usha Priya, Vice Principal Self-Supporting, for their encouragement and their words of support helped us to reach this greater height. I would like to praise, record thanks to convener Professor Kashmir Raja, Indian Science Congress Chennai chapter, for his valuable suggestions and encouragement towards the financial assistance of the conference. I take this time to thank our head of the department aided and self-supporting Dr. A.V. Joni Virgula and Dr. S. Abhirami for their constant guidance, encouragement in all our efforts taken for this conference. I thank all the faculty members for extending their hands throughout this event to make this event a resounding success. I would like to thank all the staff members, supporting staff members, to make this a memorable occasion. And I would like to thank all the staff members and research scholars, volunteers for their cooperation. Last but not the least, I would like to thank all our sponsors, Nanotech Instruments Chennai, Origelis RSI Instruments France Chennai, Nivedita Digital Studio, Trademark Academy, Bharati Agro Products Anniyur Viluppuram, Cisco Chennai. And I would also like to thank our digital platform partner, Mrs. Kavita and Balaji, and auditorium in charge Vijay, food and beverage partner Mr. Prabhu, and online publishing support Royal Book Publishing, Mr. Thirupugal. Once again, I thank you all for your kind attention. Thank you.
Thank you, ma'am. I kindly request everyone to raise for national anthem. I once again thank everyone for joining. Thank you all. We are closing the conference session. Thank you for your support and encouragement.